Hello everyone, welcome back to my channel Informatics. Today my topic will be a little bit deviated from my previous videos, as I have shown you how to calculate the electronic structure calculations using Siesta tool. And today I'm going to show you how to install and compile the Siesta as well as Siesta for your electronic structure calculation as well as transport calculations. And also the good thing about the scientific software is it gets always updated, and you have to keep the pace with it. And the bad thing about this, you have to update every time. So to keep the pace with all the computational software, like suppose for example Siesta, you need to update, and you need to also read the manual for the updates and changes, the bugs, how can you fix it, how can you troubleshoot it, and all these required some computational knowledge. And that I'm going to show you today, how to easily compile the Siesta program, because many people asked previously that how to build the software. I'm getting this error, that error, and all those things. So I decided to make one video out of it, and just to show you how to install the software, Siesta tool. And also there is a new version of Siesta which is called PSML library, which you can use the pseudo-potentials, not the previous pseudo-potentials from the Siesta database, but also the pseudo-potential from the Pseudo-dojo database, which uses the PSML version. And I'm going to show you how to build the libraries, and what are the updates and changes in the recent version of Siesta, which is 4.1 before, I guess, and the previous version of Siesta is 4.0. So there are, because I was reading the manual and I have seen a lot of changes in Siesta 4.1 manual. Suppose for instance, if you want to run the Siesta calculation in Siesta 4.0, then you have to run like Siesta and your FDF file and your out file. But in Siesta 4.1, the version has been changed, and the Siesta has been integrated with the Siesta command itself. So for the electrode calculation, for instance, you have to run Siesta -- electrode and your FDF file, and the electrode and the Siesta transport calculation can be done. So I'm going to show you what are the changes that has been previously built with 4.0 version, and now in 4.1 version everything had changed. So you need to keep the pace with all the updates and changes, and I'm going to show you. Let's get started. Thanks. So first of all, what you have to do is you have to go to the Siesta website or the launchpad of Siesta, in which you have to download the 4.1 version. And if you want to download the 4.0 version, you can download, and the compilation of Siesta will be the same for both the new version as well as the old version. So I have downloaded the 4.1 version already, and if you want the PSML support version, you go to the PSML Siesta launchpad and download the PSML revision 1 version from the website, and I have downloaded both of them. So now I'm going to show you how to compile the Siesta 4.1 version in your local computer. So first what you have to do is go to the folder, and if you see the architecture of the folder, it has the documents, all the required documents, with the inclusion of the older version also, and what are the changes that has been implemented in the recent version that you can find in this docs folder. And the main important folder that you want to focus on is the object folder and the SRC folder. So what you have to do is go to the object folder and go to the terminal in which you have reached the object folder, and the first command that you have to do is sh .src object object setup.sh. So this command will copy the object setup directory from the src directory, and it will make the compilation setup done in the src, in the object directory. So if you do the command like ls, you will find the the compilation library make file, in which the next command would be the copy the gfortran dot make to arch.make. So if you see, so now the arch.make file has been made by using the command cp. So you have copied the gfortran make into the arch.make, because your the compiler for your Mac Siesta version would be gfortran, or the library is the gfortran. So now the next command would be to compile the arch.make file in which you have generated, and just type make and press enter. So in this way, the whole library of the Siesta will be compiled over in this directory. So it will take some time to compile all the libraries, and once it completed the compiling procedure, you will find a Siesta executable in this directory. So while it is compiling, I'm going to show you some other libraries which are required for the PSML support. So the Siesta 4.1 version is different than PSML support version. In the PSML support, you need 5 different libraries, such as here, if you go to the electronic structure library ESL bundle in the GitHub page, which I'm going to give the link in my YouTube description, in which it has grid.exe component, libxc component, libpsml component, libftf component, xml f90 component, and also it has PXE solver, which I will tell you later while referring the manual. And it has also Scotch library. It has all the libraries that is required to build the latest version of Siesta, as well as the PSML support version. So once you download this by going here and download as a zip file, and I have downloaded already. So what you have to do is you have to, so since it is doing, so you go to the ESL bundle library, and in here you go to the terminal app, to the folder, and make a directory called my build. Then navigate to the directory my build and follow the instruction over here. Copy this command and just paste it over here. In this way, the whole ESL, all the components that is listed over here will be compiled in your directory. So in this way, you can compile the ESL bundle library, and all the packages can be installed in a single folder. And while compiling with other libraries like PSML version, or whatever the the softwares or the tools that require all these libraries, can be compiled by using this build directory. And you have to what you have to do is you have to give the path of all the libraries that you have installed in your my build directory, and the compilation can be done. So I will show you how my compilation has been done already. So in this directory, when you compile the ESL bundle library, so you have the XML F90 library, libxc, ftf, and I think grid.exe. So these are the and also library PSML. So library PSML, XML, F90, libxc, and I think libgridxc. These are the 4 files which are necessary for your PSML version support. Without these libraries, the PSML support series cannot be compiled. And the execution of the program that I have shown you before with the Siesta 4.1, the command will be the same. And just when you are compiling with the PSML version, when you go to the object directory and do the same command, like the sh, yeah, when you do it, and when you see that all the libraries that is required will be here, and when you see the make file, then you have to mention all these library flags over here to to be able to compile the PSML version. I think the make file is too much big, or is a big one, because the library is so big that everything will be compiled, and I think it will take some time. So as you can see in the make file also, there is the Tran Siesta is also compiled along with the Siesta version, and also the Lua interface is also compiled. That I'm going to tell you what are the changes that has been made in 4.1 version, and apart from the 4.0 version that has been previously built by the Siesta developers. So this is the way that you compile the PSML library, as well as the Siesta normal Siesta 4.1 version. So once the directory has been built and you can compile successfully, the 4.1 version has been successfully compiled, as I have shown you before. And now what you have to do is, when you go to the Siesta 4.1 version and in the object directory, when you search for the command Siesta, so you have the Siesta executable over here. So if you run .siesta, yes, your Siesta is installed in the serial version, and these are the architectures that has been compiled. So this is the way that you compile the serial version of the Siesta 4.1 version. And also there is if you done for Tran Siesta also, the Tran Siesta is also compiled along with the Siesta version. So if you type the command Tran Siesta, that will also run. So these are the ways how you compile the the Siesta executable first. Then the next thing what you want to do is, you go to the util directory, and when you navigate to this directory, you want to before there is nothing over here, because there are no executable files for the band structure plotting, CCVs, contour, contrib, and these are the utilities of Siesta. So if you want to build all of them, what you have to do is navigate to the directory and just type command /build all sh, and it will build all the required executables for the post processing of Siesta. As you can see, if you go to the bands, I think this is being done. So if you go to CCV, if you go to CML comp, your CCV's executable has been compiled, and it will take a little bit time, but it will be compiled sooner, within a few minutes, I guess. So in this way you can build all the utilities option in Siesta that can be used for the post processing of your Siesta calculations. So, and also you can individually do by going to each and every folder and just type make over here. So I'm going to show you, suppose make, and it will be done. So this is the way to compile all the libraries at once, all the utilities at once, and by navigating to a specific directory and typing the command make will make the specific executables in that particular directory. So rather than going each one by one, you can just build all the libraries over here. So as you can see, the bands, the GNU band, ICFAT2 plot, everything will be compiled at once. So this is the way that you compile all your utilities. Now if you go to the test directory, you have so many examples over here. So for that, if you go to each and every directory, you find a make file over here. The compilation is the same. Just go to the directory and type command make. So it will just it will be compiled and give you a folder called as work, and all your required pseudo-potential and as well as the out file will be there. So in this way you can find all the examples that has been listed in Siesta 4.1 version can be found in test directory. And if you go to the tutorials directory, you have the basis, the generation of pseudo-potentials by using the atom program that you can do over here. Pseudo-potentials, the basis. So in this tutorial directory you have only the pseudo-potential development program. For that you need to compile the atom program before. So test directory is the most important directory because it contains all the examples of Siesta with the latest latest build and latest examples. And if you go to the examples directory, also you have some of the few examples over here. So you have input file for the new version of Siesta. So you can refer these input files also by going to the example folder. So this is the architecture composition of the Siesta folder, in which the most important is the object folder, in which you compile the Siesta program. And the pseudos, if you want to develop the pseudo-potential by using the atom program, you can go here and just build your pseudo-potential over here. src directory is not important for you because it is the coding architecture that has been written over here. In src directory you don't want to touch this because all the libraries are here. So every time you want to compile the Siesta program, you have to go to the object directory, copy the object setup.sh to the object directory, and just build your Siesta program. Test folder with all the examples, tutorials with the pseudo-potentials, and utils will be all the utilities that you require for the post-processing of Siesta program. So this is the way that you install the Siesta program or Siesta version. And now I'm going to show you if you successfully build this PSML library, the pseudo-potentials that the PSML version use is the pseudo-dojo database. This database consists of all the PSML version pseudo-potentials which have the standard and the stringent accuracy, and it contains PBE, PBE Sol, and LDA pseudo-potentials, and also it has Onco SR as well as FR, and all the information that how this has been built can be found in the fake, and you have all the required documentation that you need to know before using this pseudo-dojo database. So as I have told you that PSML library supports is in Siesta, XML version is in Abinit, PSP8 version is for Abinit, Quantum Expresso accepts the UPF version, and I think this is for the Jupyter Notebook Python programs. So this is the way by going to the database you can download the pseudo-potentials from here and use it, and it can be only used with the PSML version of your Siesta program, not with the normal version. You cannot use the PSML in the normal version of the Siesta program. So this is the way. I'm going to give all the links of the Siesta tool that you can download from the PSML version also. And this is the library which is the most important for the PSML PSML Siesta version compilation, and the database for the pseudo-potential to be used in the PSML version of Siesta. So now I'm going to show you, when you refer to the manual of Siesta 4.0, this is the older version, in which you can see so many options, and I recommend everyone to read the manual carefully before executing your Siesta electronic before doing any electronic structure calculation. So I'm going to show you what are the changes that has been implemented in 4.1 version. And in 4.0 version, you don't have any LDA+U option separately, and also the Siesta version has to be compiled separately for the 4.0 version. But in the 4.1 version, as you can see, if you go to the execution option, so before that, I will show you. Before that, we used to do like Siesta, and we have to give the pipe like input.ftf, and then we used to give the result.out option. But now in the case of 4.1, it has been changed into there is no pipe in this, so it will be like input.ftf and your result.out. So this is the change, that this pipe option is missing over here. And also for the Siesta option, for the electrode calculation, we used to do the command called Siesta, and we used to relax it, and then we copy the TSHS file to the to the scattering region calculation, and then we have to do all this. But in this case, this has been changed into electrode option. So what you have to give is give the command is Siesta and hyphen electrode and your run.ftf. So this is the command for the electrode calculation in Siesta version. And another thing is also the Siesta run can also be done by applying the specific voltage like 0.25 or 1 electron volt, whatever you give, and just run it. So it will set the applied bias to the specified applied bias or the voltage that you want to run. And another most important thing is the before that, in 4.0 version, you have to compile the Siesta in a separate compilation procedure. But in the case of 4.1, the execution of the Siesta compilation, or the compilation of the Siesta program, also include the Siesta version. So you don't have to compile it separately for the recent version of Siesta. And also another thing is, I again recommend everyone to read the 4.1 manual carefully before going for the execution of Siesta commands, because all the input files over here, especially for the transport calculation, has been changed. You cannot use the previous input file in the Siesta 4.1 version especially. And also there is this PEXI solver, which is used for the MD simulation package, which I also don't know, because I have to test it first, then I can make a video out of it. And this is for the spin polarization or something, I don't know regarding this. Just I have to look into this. This is the pole expansion and selected inversion method, which is a fast method for electronic structure calculation. based upon Kohn-Sham density functional theory. I don't know, I have to read about this because this as instructed by the manual, this PAXI can be used in the external packages like the big DFT, CP2K, DFTB, ESL Bundle, Quantum Wise in Siesta also. So I have to check what it does, and once I execute it successfully, I can make a video out of it, and what are the advantages of using this PAXI solver might be beneficial for all of us. And also there is another, the change in here is it has included a specific LDA+U section in which they have mentioned how to use this LDA+U tag in your Siesta input file, which is really good because in the previous version it has not been there. Only they have mentioned the LDA+U tag you can use, but now they have included in a more descriptive manner that you can find. And regarding the Siesta, everything has changed. Everything over here, the input file is also changed. So now you have to run the electrode like this command that I have shown you before, and also the input file which I was mentioning, and you can find the input file in the test directory over here. As you can see in the test directory, you have the TB trans and Siesta. So if you go here, you have your input file specified over here for the for all the calculations. I think, yeah, you can find the examples over here in the TB trans, which is really quite complicated rather than the 4.0 version, because in the 4.0 version it was straight, that I have mentioned in my video. It was easy to do the calculations, easy to prepare the input file, but in 4.1 it is kind of difficult, but you can try by your own. So these are the some of the changes and the way that you can compile the Siesta version is by using those commands that I have shown before. So so in my next video, I think I am going to show you how to use this PAXI solver as well as the Siesta input file, how to create the input file for the new version of Siesta, which is I think quite good. And also I'm going to show you how to do a vibrational phonon calculation by using the latest version of Siesta. And another most important thing is, so the Mac users, the compilation of Siesta is quite straightforward, and for the Linux also I think it is quite straightforward, but for the Windows I don't know because I don't use Windows at all. And those who have been using Windows and Siesta version, so please go through the website or the manual how to compile it. And also there is another option to get the Siesta libraries installation of Anaconda library, and you find you download the Anaconda for your specific version like Windows or maybe for the Linux or Mac. And if you and in the Anaconda cloud you can find the Siesta package, and that you can install by using the command line or by going into the launchpad and just type Siesta and just install it. So they have the default version for Siesta 4.0.2 that you can install, but you cannot install the 4.1 version, and the 4.1 version can only be installed by using the commands that I've shown before. So good luck with your installation and compilation of Siesta, and let me know in the comments that what you have been facing the problem. And also I recommend everyone to go through this library, that you find all the packages required for all the electronic structure calculation libraries over here, and compile it, and you will be benefited from this. So thanks, and I will see you in my next video with some other more interesting things. Thank you. Hello people, welcome back to my channel Informatics. As I said in my previous video that I am now back to make some tutorials for you guys, because I have seen so many comments in my YouTube videos previously that I made, and some of the queries that I was unable to answer them or make a video out of it. But now since I'm back, I can make the videos out of it. So I will start with the first video, which is called the Siesta installation procedure. I'll show how to install all the libraries without so much hassle, so much hectic procedure to install a single library one by one to install the Siesta program. But this will be a straightforward video, and you don't need to install all the libraries separately. You just have to follow my guidelines exactly, particularly the same way that I'm doing right now. I'll be doing in Ubuntu, of course, because many users, many Siesta users, they prefer Ubuntu rather than Mac or maybe Windows. So in Ubuntu, what I'm going to show you is how to install all these libraries in one package, and you can install this Siesta very straightforward. But some of the prerequisites that are required to install all these libraries, I'm going to show you. And please follow the guidelines exactly the same way as I'm doing here today, and you can do it. So let's start. Thanks. What you have to do is you have to go to the website of Siesta, or maybe just type how to install Siesta PSML version, and then you can find this tutorial, and in which you have to install all these libraries called library PSML, library grid XC, XML F90, and lead XC. These are the 4 libraries that you need to install in order to run the Siesta PSML versions, not the normal Siesta version. So this Siesta PSML version is nothing but it uses the Pseudo-potentials from Pseudo-potential Database that I previously mentioned in my all the videos, how to use the Pseudo-potential of PSML library. And for that you need all these 4 libraries which are required. You can install one by one, and that is a little hectic procedure to install one by one, but I will tell you one simple way, as I previously mentioned in my videos, but I have not elaborated my the installation procedure. But today I'm going to show you what are the prerequisites that are required to install this Siesta PSML version, as well as all these libraries, and what is the package name. The package name that I'm going to tell you is the electronic ESL Bundle Library. So you can just search ESL Bundle Library and go to here, Electronic Structural Library ESL Bundle, and then you download this code. And before installation of this bundle, you need some of the prerequisites in order to install the Siesta PSML version. So that I'm going to show you now. So open the terminal and paste this code. These are the prerequisite tools or libraries which are required for the Siesta installation procedures. So the first command for which you want to install all these libraries, I'm going to paste it. So please note down this: sudo apt install build -essential g++ g fortran lib redline -dev m4 xsltproc -1. So this is the first prerequisite that you are going to install. So I'm going to press the enter, and it will, of course this is a sudo one, so you need to enter the password, and this will be installed. So I have installed it previously, so I don't have to install it again and again. So this is for the serial version of the Siesta PSML, or maybe Siesta normal version as well. But if you want to install MPI libraries, then you need to deploy another command. I'm going to paste it here, so make it clear. So this is the command to install OpenMPI. Those who have want to use these OpenMPI libraries, you can install this package, sudo apt install OpenMPI-common, OpenMPI-bin, library OpenMPI-def -y. So this is especially and particularly for the Ubuntu platforms. Remember that. So if you press enter, then yes, I have already installed it. There is another command. If you want to install MPI-ch, then you can further deploy another command. But if you install this OpenMPI, that is enough to run the Siesta, or maybe install the parallel version of the Siesta. So these two things are really helpful in order to compile the code of Siesta and other DFT packages as well. So you need to install these prerequisites particularly. So please follow my instructions, and first what you do is open the terminal and put these two commands. I will write in the comment as well all these commands, so that you can there will be no problem in installing, there will be no problem in finding the commands. So I will put it in the comment section as well. So this is the first thing that you want to do. So this is done. Then download the package called ESL Bundle Library. I think it is in my download. Yes, ESL Bundle Libraries. Okay, so go here. What you want to do is, okay, I'm going to close this. So here what you want to do is you have to make a directory called my build directory, or any directory, whatever you name. Suppose I'm going to make my directory called Preetam. Okay, so I made a directory named as my build directory or Preetam or something like that. And then what you go to cd Preetam. So it is better that if you just type my build directory as provided the instruction from the ESL Bundle Library GitHub package. So you follow that thing, and I have already made this directory my build directory. Actually I have installed the ESL Bundle Library this morning, and I was trying to compile each and every code, whether it works or not, and it perfectly works for the serial version of the Siesta if you want to install in the laptop or maybe in your computer, somewhere like that. So it's better than you just type my build directory. Okay, so I'm going to go there. Suppose cd my build directory. Okay, so I'm there, and what you want to do right now is to there is another prerequisite thing that is required to install this ESL Bundle Library. That is also I'm going to show you. So that command is nothing but the Python 3.8 dist utils. So I'm going to paste that command over here so that you can know what you want to install. So this is the command sudo apt -get install Python 3.8 virtual environment Python 3.8 dist utils. So this is the command that you have to install in your computer if you have Python 3 version. So this is a sudo command, so that you have to give your password. So I have already installed it, so please remember this command. I'm going to write all these commands in the comments as well, but please follow these guidelines. Okay, so you are in the my build directory. So the next command that you want to impose to install this ESL Bundle Library, as I have shown you, that you need to have all these libraries at once installed in your system. So if you want to install one by one, then you are welcome to do that, but I don't think so, because nowadays many people are so convenient and they are lazy enough so that they don't want to install everything one by one, so they need something sophisticated package to install everything at once. So this is the package that I'm going to tell you, which can install all the libraries required for your Init installation, for your Siesta installation, and for many other platforms. So the next command that you want to impose over here, if you want to install this, let me check. Okay, so the command is // install, and if you press tab, there it will automatically open // install -bundle -s. So you want the help command to know what are the commands that is required to install all the libraries, particularly for the Siesta. So if you see, they have -c is for the compilers. If you have GCC Fortran compiler, you can use this GCC command, -c GCC. And if you want to install the MPI version, I have not tried this, but you can try this at home if you want to install MPI libraries in your supercomputer, or maybe somewhere like a big server. If you want to install in the laptop, then just use the serial version of the Siesta, not the parallel version of Siesta. Please install your serial version of Siesta in your laptop, because your laptop is not a server. So if you are going to install MPI version, there is of no use. Okay, so the first command is -c GCC. The next command is -m. What you want to install? If you want to install Siesta, you want to install ESL Bundle Library, or you want to install Init package. So in my case, it will be -m Siesta and -n and your particular OS. So I'm using Ubuntu, so I will use the Ubuntu architecture. And there is another option called no interact, that you don't need to press every time. If a system package failed, you don't have to type a number or a button. It will show interactively. So you don't want interaction or something, you just want to run it by itself. So let me put install bundle -c GCC is my compiler, -m I want to install Siesta, and then -s your operating system is Ubuntu, and you don't need interactive window to install ESL Bundle Library. So no interact, and that's it. Press enter. It will automatically I have already installed it. I have tried in the morning and it worked perfectly for me, but there are some tricks how to compile the Siesta program as well. So it will go on and it will install all the libraries like this. Let's see. So if you go to my build directory, there you will see all the libraries it is installed. So your packages will be in the install libraries, where you have all the required packages like library PSML, library gridXC, XMLF90, and libxc. So if you can search for any package like library PSML, then you can find over here, yes, here, see library psml.a.so, and these are the configuration packages. So if you want to find something called XMLF90, yes, it is there, the package is here. So there is also a program called matrix switch that is also there, and I think what are the other packages called PSML, yes. So this is a Siesta PSML version, so you need PSML.a. So it will take time at first, and please remember that you need to put all the 3 commands that I have shown before. See, everything has been compiled successfully, so everything has been done. Because I have done it previously, it doesn't took so much time for me to install the ESL bundle library, but now it's installed. Okay, so you just get out of that And what you need to do is you need to check in the my build directory, install, and in the library whether all these packages have been installed or not. So if they are installed, that means your ESL, all the libraries required for the Siesta package has been installed. The next thing what you want to do is you need to go to the Siesta server, and you need to install you need to download the Siesta PSML R1 version. So once you download the Siesta PSML R1 version, go to the object directory and just open a terminal out of there, and you can just extract one of the object setup.sh file out of that. So I'm going to in the object directory I'm going to make another folder called, so this is for your for the tutorial purpose, but what you can do is you inside the object folder you will deploy all the commands that I'm going to show you. So I'm going to make a new installation out of that, so you don't have to worry about this. You don't have to make a folder called serial or parallel or something like that. You just install everything under the object directory folder. So this is so I'm going to navigate to the serial directory, and the first command that you need to install is src object setup.sh. So the double dot, the directory I was referring was to go back to the object directory and then go back to the src directory. For your case, the command would be simply src object setup.sh, object setup.sh. Since I am installing everything inside the serial folder, I have to navigate 2 times, but in your case it will be only 1 time. So dot dot, so this will be the command for your purpose, and for me I need to navigate 2 times. Object setup.sh. Yes, the compilation has been done. So the next thing what you have to do is mv g port run. Oh, let's see. Yes, everything has been here. Maybe let's check. The next library, I mean, I have shown it previously to the Siesta users that how to install that. So in the object directory there will be a arch.make file. Yes, this arch.make file. This I am going to attach in my comments so that everyone can download this, or I can copy all the requisites from here. Yes, everything from here. So I can just copy in and paste it over there. So what you want to do is I just copy this arch.make.file and put it in the serial here inside this folder just to test it. So arch.make file, the architecture of arch.make file should be clearly mentioned, and this has to be particularly more specific towards the libraries and towards the root directories of all your PSML, XML F90 and everything. So since you have installed the ESL bundle library, now what you want to do is I'm going to show you ESL bundle. Go to the my build directory, okay, and then go to the install folder. So the here you don't have to change anything. This will be in general. So now here you want to define the PSML root. So this will be download ESL my build directory install. So inside the install folder everything is there, library, your include, your share, everything is there. So just you have to mention the path of this install directory, and that's it. So this will be for PSML root, XML F90 root, gridxc root, libxc root. Everything has to be that particular directory, and that's it. You don't have to change anything else, just include this. And the next thing what you have to do, you have to comment this comp_library section. You have to comment this. In the default arch.make it will be uncomment, so you have to comment this. You don't need this. right now. And the three things that you have to define in your arch.make file is this: TEFS is equal to hyphen dgrid underscore dp, TEFS is equal to hyphen dhav underscore libint, and DEFS colon is equal to $ defsmpi, defcdf, and defs. So these things you have to mention. These three lines you have to mention in the arch.make file. And the other thing that you want to mention here is LA-pack libraries. So for this LA-pack libraries, if you want to install the LA-pack libraries, I'm going to show you the command in which you can install the LA-pack libraries. So for this, just you have to execute this command: sudo apt-get install libblastdev lib lapack.dev, and that's it. Just give a password and all these libraries will be installed. Since I have previously installed this has been, it is showing that okay, it is already there. The path of this LA-pack libraries in general in Ubuntu is this one. So I'm going to attach this file in my comment so that you can use exactly this file if you follow my tutorial. And that's it. Just you have to type the command called make, and that's it. It will be done. So now it is going. It can show some warnings because we don't know the architecture of this Siesta program, because you are not the coders. We just follow simply the steps given by the Siesta users and the Siesta community. So we follow the exact same tutorial, but this is the simplest way if you install the ESL bundle library and just make it happen in your laptop. So there is another trick. After this installation of Siesta, if you go to the Siesta folder, download Siesta folder, then go to your object directory. Since I'm installing in the serial version, so I think everything will be there. So there will be an executable of Siesta, so that you can just type /Siesta and Siesta will run. So before that, there is one trick that I'm going to tell you. After this installation, I'm going to tell you what is the trick and where are the libraries, why you get such kind of errors. So there will be one error called shared library error. So every time when you run this Siesta, so after this installation, then you will get an error called error in loading this library, something called library.so, library.so.0.0, something like that. So you will get those errors. So to rectify that error, you need to do another step. I'm going to show you after this installation. I think it will take some time. Yes, it is building the Siesta version, so it will take some time. But once it is done, if you since I previously installed the Siesta, I have defined all the libraries and all the path and all the correct libraries for this Siesta to run. So remember that this is a serial version of Siesta. This is not an MPI version of Siesta. So now everything has been done. So everything has been done. So if you install the Siesta, without any errors, so you will see that see this command, end of reference section. That means your Siesta has been installed. So if you go here and just find out Siesta, yes, there will be 7 MB of executable. So this is your executable. So if you just type Siesta, yeah, it will not run. So it will give you an error called error while loading shared library. So I'm going to show you again why this error comes. So if you just type Siesta, you will find this error. Siesta error while loading shared libraries, libxc f90 so.5. That means this file has been present here in ESL Bundle Library. If you go to the my build directory, install, and if you go to, I think not include, but libraries, yes, all these libraries, there are these so files. So if you find libxef90.so.5, so you will find it here. Yeah, this one, so.5. So this library, it is unable to find this library. So for that reason, what you have to do is you have to export the path of this particular library. So I have made that comment previously, so I can show you. Yes, so the command to rectify this error would be export ld_library_path is equal to $ld_library_path : and your path to the install library version. So this, so if you go to install and this library, so this library path you have to give to this ld library path, and that's it. Just type this and clear it out, and now run Siesta. See, it ran perfectly. So these are the small tricks that you need to do before installing ESL Bundle library as well as Siesta parallel version. I mean Siesta serial version. Serial mode. So this is in serial mode. Okay. So now you can run your Siesta and enjoy. Thanks, and I will see you in the next video. Since I have uploaded the previous video regarding the questions, the queries that I need from you, what to make the other videos. So this is my first video. Since many people have commented on my Siesta installation video, I have, I now made this video for you all to troubleshoot the errors that you are getting while installing the Siesta. So these commands, so please follow this video particularly, and then you can easily or without any hectic, you can just install the Siesta without the need of installing each library separately. So please follow this and enjoy your video. Thank you. Back to my channel Informatics. Today I'm going to show you how to generate pseudo-potential for Siesta program by using Atom program, which is given by the Siesta community. When you search for the pseudo-potential for Siesta, they provide you a link to download the Atom program, which is for the academic user. And all the Siesta pseudo-potentials that you are searching for, which is provided by the Siesta website, are developed by using the Atom program. So they also provide you the choice to generate your pseudo-potentials by yourself, and also they provide some default pseudo-potentials which you can try and test for electronic structure calculation and compare different band gaps, lattice constants, etc. Whatever the parameters you need, you can test it by using those pseudo-potentials and the pseudo-potentials that you can develop. So what you have to do is, first you have to go to this website which is provided by Siesta program, and download the Atom program by accepting the license, and download the program. I have already downloaded the program over here, and I'm going to show you how to install the program also. And also one more thing, that when you search for the Siesta pseudo-potentials, you get this website and as well as this website. I think this is something provided by NNIC, and you can, over here you can search for, suppose you want to search for the oxygen pseudo-potentials, then type O and search, and you find different types of pseudo-potentials which is available for Abinit, Quantum Espresso, Qbox and Siesta. So when you search for it, so you have two options. So one is the LDA Pseudopotentials, another one is the GGA Pseudopotentials. So if you want GGA Pseudopotentials, then you have to click over here and then copy this and save it as o.psf. And the other way is yes, this one, the upper one, where you can find the LDA Pseudopotentials. So how can you differentiate between these two, because these two look similar? For that, you need to see the first line, in which it is given the element, that is oxygen. Ca is the LDA Ca. These are the authors that have provided the LDA and Ca. NRL, I think, is non-relativistic, and about NC, I don't know about the NC. And these are the radial cutoffs, you can see. So you can differentiate by using the second parameter, which is Ca. This is for LDA, and for GGA, I think it will be for PB. So in this way, you can differentiate between the GGA and the LDA pseudopotentials, and you can test by using your own parameters and calculations. So this is a good website to start off with. And if you want to generate your own pseudopotentials, then you have to download the Atom program from here. And one more thing you have to do is you have to also download this ESL Bundle Library, which I will provide you the link after the video in my description, in which you have to download this. I have already downloaded the program, and also I'm going to show you how to install the program. So what you have to do is when you download this program, then go to the terminal and make a directory. Suppose build directory or something. Then navigate to the build directory, and what you have to do is put this command /jhbuild.pyld, and that's it. You can install all the libraries which is required by the Atom program to compile. And so I'm going to stop this because I have already downloaded it and I have installed everything. So you can try yourself, and you can install all the libraries which is given by the ESL Bundle Library. Why this is important, that I'm going to show you while using the Atom program to install. So I'm gonna keep it this side, and I'm going to show you how to install this. When you open the Atom program, so there will be a arch.make.sample file, in which you have to mention all the files. So I have already mentioned in my file that I'm going to show you. So this arch.make.sample, you have to rename it to arch.make, so that when you execute the make command, it will run. So when you open the arch.make, you have the options. So I'm going to make it big. Yes. So this is the arch.make file, and you have to define your architecture. In my case, it is Mac OS G Fortran. So I have defined my architecture, and the required libraries to install the Atom program are XML F90 and libgridxc, which can be obtained individually. You can install it individually by obtaining the program by just googling it. Yeah, you can obtain the program and compile it, but rather than compiling one by one, so the best way is to get the ESL Bundle Library, in which you have all the programs. So here it requires XML F90, you have the XML F90 library, and libgridxc, and you have the library libgridxc. And for other options also, like this is for the PSF generation, pseudo-potential generation in the format of .psf. But if you want in .psml format, there are other libraries which are required, which is called library PSML and libxc. So you have many options. You can individually download it, or you may download the bundle library, in which you have all the libraries that is required for electronic structure calculation and pseudo-potential generation. So this is the best way to do. So in this file, now you have to give the root of XML F90 root, in which I have over here XML F90. So my the path to the my build directory and your XML F90 directory. So this directory I have given the path. For the libgrid.xc also I have given the path, exactly the same path. If you want to test it, I can show you. So when you get this, you have users, Pritham, ESL Bundle Master, my build directory, libgrid.xc. So users, Pritham, ESL Bundle Master, my build directory, and libgrid.xc. And also the same for the XML F90 also. Yeah, the same. I have given the description. The other thing what you have to do is you need to also give the .mk files, which is required for the Atom program to be installed correctly, and generation of pseudo-potentials can be done by using these two libraries. So this XML F90.mk and gridxc.mk will be found in the config directory, in which you have the data and your XML F90.mk. Similar way, you have the file for the gridxc. Go here, config, data, and you have your gridxc.mk. So you define the path exactly in the similar way, and I'm going to close this and open this, go to the terminal, and remember to make it arch.make. So just type make over here, and it will run and it will install the Atom program for you, in which you can, in this directory itself, you can generate your pseudo-potentials. So yes, it is done. So this is the way to install the Atom program. And yeah, these are all the, and this is the executable Atom, but you don't require this at all. So now for the pseudo-potentials, so now we can move into the pseudo-potential generation, that I will show you how to do it. And before the pseudo-potential generation, there will be a tutorial file in which you have the option called PS generation, and the utils files consist of all the scripts that is required to generate the pseudo-potentials. So these are some of the test examples given by the Atom community to test your pseudo-potential. The most simple example is the Si silicon, in which you can test your pseudo-potentials, and you can also plot those things. So the next thing I am going to tell you is how to generate the PSN. So I'm not going into the all electron part, because you can read the manual how to test your radial cutoffs and core corrections, non-linear core corrections, etc. So one of the important aspect before generating the pseudo-potential is to one needs to start with an electronic configuration of the atom. You should know the electronic configuration of the atom, and usually it is the ground state, but it need not to be so. And in some cases, one needs to artificially populate an orbital which is empty in the ground state, and just so that the corresponding angular momentum is represented in the pseudo-potentials. For example, when you consider the silicon, it has the ground state is 3s2 and 3p2, the valence electrons. But if one uses that configuration to construct the pseudo-potentials, only the S and P channels will be generated, so which will be not enough to consider a full pseudo-potential generation. So for that, what you need extra configurations such as 3s2, 3p, 3p, and also 3d, which you can see over here. in which you have I will tell you what are these things. So when you open the directory, SI directory, and go to the si.tm2.inp, this is the file for which you are going to generate the pseudo-potentials, and what are the things which are present over here that I'm going to tell you. So this is the input file, which is extended by .inp file, and this is the pseudo-potential generation command, that is PG, which is pseudo-potential generation, and this is your element in which you are interested on. So I am taking the example of silicon, and this is your element symbol, chemical symbol of the atom, and this one is, I think this is CA. Yes, this is yeah, CA means this is an LDA algorithm, and you can use different types of option. I'm going to list out the options over here. So you can use CA for LDA, HL is for again LDA, GL is again for LDA, PB is for PB, GGA, RV is for GGA, RP is for again GGA, which is RPBE, and PS is for PBE sole GGA, and WC is also for GGA, and BL is again for GGA, which is BLYP. AM is for AM05, which is again GGA, and these are all the GGA options from PB, RV, RP, PS, WC, BL, and AM. CA, HL, and GL are LDA options, and the van der Waals option will be VW. So these are many different types of options that you can give for over here. You can give over here to generate the flavor of pseudo-potentials. If you need LDA, you provide the three first options, and then the rest of the options for GGA, and the last one would be for the van der Waals. So remember this. Now when you move forward, then you have this one, you have to default, you have to mention it default, and yeah, this line should be there, and this is your principal quantum number, this is your angular quantum number, and this one is the occupation, which is spin up and spin down, spin up and spin up and spin down, and the first line would be the number of core and number of the core, and this one will be the number of valence orbitals. This one is your principal quantum number, this one is your angular quantum number. So the first line has to be represented as the core orbitals, and the second option would be the valence orbitals. So this is mostly important, and this one is your principal quantum number, this one is your angular quantum number, and the last line would be the cutoff radii that you are going to mention. So these are the cutoff radii for the 3s, which is 3 principal quantum number, and 0 is your angular quantum number. So angular quantum number for s orbital is 0, p is 1, d is 2, and f is 3. So for 3s is 1.90, and 3p is for 1.90, 3d is 1.90, and 4f is 1.90. In this way, you don't have to change even a single line also, and these things has to be the default lines that you can mention, which you can find in the example folder, and you can generate your pseudo-potentials on the basis of that. So this is the input file that is required to generate the pseudo-potential. So why this configuration is needed? Rather, you can stick for the silicon until 3s2 and 3p2. But why the extra parameters are required, which is consideration of the d orbital and f orbital, is because the appearance of the fractional occupancies should not scare you. Remember, we consider the electrons only through their charge density. That choice is more or less arbitrary, although sometimes it helps to know something about the environment in which the atom is going to find itself in the solid state calculation. We would prefer an ionic configuration for sodium to do the calculations for the sodium chloride, for example, for instance, you say. So in any case, whatever the starting configuration, the pseudo-potential by definition and construction should be basically the same and should give equally satisfactory results when tested in any up to the limit explored in the by the examples given by the Siesta community or the Atom program. And do test all the pseudo-potentials configurations by defining all the how many core orbitals that you need to consider, how many valence orbitals you need to consider, and what would be the configuration rather than the standard ground state properties. You have to consider for the pseudo-potential generation the d and f orbitals also. So, and also you can parameterize the radial cutoffs as well as the radial cutoff distance. You can test. So in this case you have taken 1.90 and you can test it for 2.0, and after generating the pseudo-potentials you can verify it by plotting the diagrams that is mentioned in the end of manual, or maybe by using your own guesses. If you quite good in physics, then you can basically know what you are doing. So this is the way that you can generate your pseudo-potentials. So I'm going to tell you how to generate the pseudo-potentials by using what command. So this is your input file, which is in the directory of the tutorial and SI in PS generation. So the next thing what you want to do is go to the command line on the same folder and just press --utils, and this will be, I think, pg.sh, which is pg is for pseudo-potential generation. This is a script file already present in the utils directory. You can find over there, and after this you have to give the input file tm2.inp, and that's it. And the pseudo-potential has been generated in three formats. One is VPS, which I think you can use for any other program. PSF you can use for Siesta, and PSML is used for the Siesta PSML version. So these are the three things, three pseudo-potentials that will be generated. So I'm going to show you the PSA format, which is normally used by any Siesta program 4.0 or 4.1. So it can give you the element symbol, and this will be your CA, means you have generated the LDA pseudo-potentials, and this is the radial cutoffs for different orbitals, the valence orbitals, and this is your pseudo-potential file. So now you can copy this pseudo-potential file and test it by using Siesta input file. Follow my previous videos in which I have mentioned you how to generate input files and how to run a Siesta calculation for electronic structure calculation. And you can test these pseudo-potential can be tested by producing band structure, DOS plot, the lattice constants, etc. you can plot. So these are the pseudo-potentials that have been generated, and another folder has been generated which is by the same name, si.tm2, in which you have many different files that I'm going to tell you. So the most important file out of it, I mean, you can explore all the files. I am not going to tell you each and every file over here, but you can explore the different file architectures and file contents by getting through the Atom manual. But the most important thing over here is your some of the scripts has been already present in the utils directory. So you go to the command line, and by using GNU plot you can plot the charge.gplot. The most important file is charge.gplot, which you can find over here, I guess. Yes, this one, charge.gplot. So I'm going to plot this, and I'm going to tell you what it means. So the command would be GNU plot hyphen persist and charge.gplot. Yes, when you click this, there will be a graph in which you have four types of lines, I guess. The first one, I think this is the violet one, represent the all electron core charge, and the green line represent the all electron valence charge, and PS means pseudo-potentials that you have generated now. So this will be the I think this is the blue line for the core charge, and the pseudo-potential valence charge will be the yellow line. So you can see that the PS, I mean the pseudo-potentials, and the all electron valence charge densities are equal beyond the radial cutoffs. The radial cutoff that you have given is 1.89, so you can see that both the charge densities are the same. And in this way you can test your pseudo-potential, whether you what you have generated, whatever the radial cutoff that you have given, whether it is correct or not. You can verify by using this plot. And there will be another plot in which you can which is called as pots.gplot. So again you have to plot this persist gplot. So yeah, this will this one will give you, so VS means I think, oh sorry, this is the orbital valence charges, I guess. Yes, orbital valence, which is for s orbital, p orbital, d orbital, and f orbital. So after the cutoff, which is I think 1.89 over here, you can see all the lines that merges beyond the largest cutoff radius, and the pseudo-potential tends to minus z by r. So which is quite good. And in this way you can test your pseudo-potentials. And also remember one thing, that the radial cutoff distance that you have given is in Bohr, so you have to carefully consider that also. And yes, and also you can explore many more things. So one of the way, I guess, is to compare the all electron eigenvalues to the pseudo-potential eigenvalues also. So for that you can do grep command by looking into the out file. So the command would be and v out. So you have by using this command you can see that these are the eigenvalues. These are the eigenvalues for your all electron as well as for your pseudo-potentials. So you can compare it. And remember one thing, the eigenvalues for the all electron and the pseudo-potentials eigenvalues will not be exactly identical, because the pseudo-potentials are changed slightly to make them approach their limit tails faster. And also these pseudo-potentials that you have generated are or can be transferred from one program to another program if you define the radial cutoff carefully. And there is another point, is that the larger the radial cutoff, the lower the degree of the transferability, but the pseudopotentials will be softer. By softer, that one needs fewer Fourier components to represent it in the Fourier space. The price of the higher transferability is a harder pseudopotentials. So it depends upon the degree of the transferability. Because of the radial cutoff distance, the larger you take, the softer will be the pseudopotential. The smaller you take, the harder will be the pseudopotentials. So this is the way you can generate, you can explore all the files over here also. So the most important file over here is pots.gps, and another one is the charge.gplot, and you can compare by using GNU plot. And also you can explore all the files over here, which you can find in the Atom manual. And these are the pseudopotentials. This is the PSML version, which you can use for Siesta PSML version R1, and this is the PSF version you can use for Siesta, and I think VPS is also used for Siesta. I don't know, you can check. So these are the ways that you generate your pseudopotentials. You can test with other examples. I have tried only the silicon, so you can test with all the examples. If you go for the FE, there are so many possibilities. There is a spin INP. This is for GGA. This is for GGA, which includes the core corrections also. So that will be represented by R core, semi-core pseudopotentials. These are, which are good actually because they provide good band gaps. And this is with some other configuration. You can test all those examples. And thank you for watching, and hope to meet you next time with some other more fun tutorials using Siesta. Thanks. Hello everyone, I am Preetham from Uppsala University, Sweden. I am a PhD student in the Department of Physics and Astronomy. Currently I am doing all my DFT calculations using Siesta, and those who are Siesta users, I can show you how to make an input file by using automated software, because people usually, those who are Siesta users, they create their input file manually. So today I'm going to show you how to create Siesta input file by using an automated software, which I'm going to show you. This is my first tutorial video on how to make an input file using Siesta. So let's get started, and I hope you like it. Thanks. First, what you have to do is you have to go to this materials project site and download choice of your material. For me, I'm inputting this zinc oxide as I'm working on it, and I select this one, crystal structure, and you have to download in Posca or maybe using the WASP format, which I've downloaded already, as you can see here, this one. So if you open it, so this is my crystal structure, and I am using this Crystal Maker software, which is really good to produce publication quality figures. And although it is a commercial software, you don't have many options for the Siesta users, as you don't have any export features for the Siesta software. So you have for the WASP software, you have as a PDB molecule, PDB crystal, CASP, CAM3D Cartesian, DL poly, etc., etc. but you don't have in any of the software. Although if you open in Vesta also, you don't have any option for the Siesta users. So for that, we need to download the software called WX Dragon, which has many more features, which is an executable file which I've downloaded already, and I can show you how to input the structure. So this is the interface for the WX Dragon. Here you open the structure and you have the visible window, and here there is an export button in which you have so many features, so many export features for different types of softwares, in which CSA is one of the format. So you have VAS, you have XYZ, FPLO, DL poly, everything. Whatever you need, you have quantum espresso, PDB format, etc. But for this tutorial, we are going to deal with the Siesta input file. So if you click it and you apply it, and you have the input format. So this is the basic input format of Siesta, in which you can save to a file. And the Siesta accepts the input file in .ftf format, and you can input the file for Siesta and do your DFT calculations. So this is the basic format for the Siesta, in which you have system name, system level, number of atoms, number of species. This is the block of chemical species level, lattice constant, lattice vectors, and atomic coordinates with species numbers. So this is one of the one of the format, one of the Siesta format, in which you have to input all the atomic coordinates as well as the species numbers. For thousands of atoms, it is really very difficult to input it manually. So for that, this software might be useful, and you are ready for your DFT calculations. So that's it, and in the next video I can show you after a successful DFT calculations how to plot a band structure and DOS plot by using GNU plot. Hello everyone, welcome to my next tutorial. In the previous tutorial I have shown you how to create an input file for Siesta, and today I'm going to show you how to run Siesta locally by creating input file with specific commands for the band structure, PDOS, DOS, etc. For specific materials. After uploading my first tutorial, some of my colleagues they requested me to run the Siesta locally, and I have decided to make a tutorial out of it, and hope you like it. Thanks. So let's get started. What you have to do first is you have to go to the materials project site and download your specific materials, as one of my colleagues suggested, to work on this material and this one. So what you have to do is you have to download the VAS format or postcard format, as I have already downloaded both of these materials. And the first thing you have to do is you have to visualize the materials by using the software WX Dragon, as I have suggested that it can create an input file for Siesta. So you have to open it. So this is the material, and go to the export and click Siesta, and you have the input file for Siesta. So save to a file, and do the same for the other material. Open the file, open the postcard format and export Siesta input file. So these are the two input files for two types of materials, and the most important thing is you have to label the materials, the system name, and you want to label it like as you get the outputs on the basis of this name. So you can define it as Siesta relaxation something. So number of atoms is 15, number of species is 2. These are the chemical species level, lattice constant, these are the lattice vectors, these are the atomic coordinates and the species numbers. So this is the basic input file for the Siesta to run a DFT electronic structure calculations. So now I'm going to show you, I have created a GitHub file in which you have three different kinds of FTF file. One is for relaxation, one is for DOS, and one is for benchR. So for the relaxation, you have several options you want to input in your input file, in which you can specify the on-cost pack. Until here, everything is similar as created by WX Dragon. But then you have to specify the on-cost pack, K points, mesh cutoff, basis type, basis size, energy shift, functionals, what you have been using, iterations, and solution method. These you can find it in the Siesta manual as well. And these are the some of the options that you want to, that is dependent upon your choice, what you want to do it. And for the band structure analysis, you have to input this column to create the band structure. And so in this Siesta input file, what I'm going to do is I have to, this is the basic format that you can run your calculations. It accepts all the default parameters from Siesta, but if you want to specify specifically all the parameters, then what you have to do is you have to input it manually, as Siesta provides many options to modify your results or modify your input file. So what I'm going to do is I will input all those parameters in here. Suppose it may be you want to specify 10, and self-consistent field, $400 ROI, SCF iterations maybe 1000, or you can specify by your own, and MD type of from CZ. If you want iterations to get a converge value, iterations something around 50, and if you want your band file to be written, and there are several outputs that you can specify over here. And if you want the charge analysis, and then you can write Mulliken pop as 1. These are some of the options that you can explore. And this is the band line scale you can specify also. And remember to when you input this when you create this input file for Siesta, you have to specify some blank lines over here, otherwise the Siesta won't run. So this is the main aspect of this. So this is the file that I have created, and you can refer to my GitHub account. Here you have many options over here, and you can refer the Siesta manual for different types of input files that you can find according to your choice. Now the second most important thing is you have to specify the pseudo-potential files, which is I'm going to use GGA PBE correlation functional, as I have mentioned over here. Yes, as I have. So you can see I'm using GGA PBE, and for the specific GGA PBE pseudo-potentials, you have to go to this website, and you have the LDA option as well as the GGA option, and Siesta usually accepts the PSF format. So you have to find the correct pseudo-potential file, which is GGA PBE. In my case here is SE. So you have to download this pseudo-potential file, and as I have already downloaded over here, see these three pseudo-potential file as I have already downloaded. So you have to paste it over here, not this one. This one is for this. And these are the files which are necessary, not this file, but these three files are necessary to run a DFT calculation in Siesta. So now I'm going to show you how to run Siesta in the program. As I have already compiled Siesta in my local computer, you can also compile Siesta in your local computer, and this is the Siesta executable file for the Mac, and you have so many tutorials how to compile Siesta in your local computer. I'm not going to do that, but now what I'm going to do is I will run this Siesta calculations based upon what I have created an input file with these pseudo-potentials GGA PBE, and the command is Siesta the executable file with this sign, and your input file siesta.ftf. And if you want to monitor your output file, then you have to input this result.out and press enter. Oh, I think something happened. I think there is some parameter that is, oh, okay. Parameter. Now I can run it again. I mean, you can specify your input file, and yes, started running. So this is the way how you create your input file for Siesta, and collect all your pseudo-potential file. It may be GGAPB or LDACA, whatever you want. You can just input it and refer to the Siesta manual for the convergence criteria. Also, to specify mesh cutoff is one of the convergence criteria. On cost back, cake points, one of the convergence criteria. You have to run many iterations to converge your calculations. And mesh cutoff parameter, you have to get a converged calculation based upon a unit structure, and then you can specify your mesh cutoff parameter. Also, basis sets also is one of the convergence criteria for Siesta. What you have to do is basically converge your basis size and basis set optimization, you can call it. There are many options. You can refer the Siesta manual for that, and that's it. This is how you create your input file and run Siesta by using your local Siesta installation, or you can refer to any supercomputing cluster so it can run faster. As this is a serial mode installation of Siesta, so you can run it. I mean, it will take time, but when you run it in a supercomputing cluster, or you can run it in parallelly, then it will be much more faster. Okay. Thank you. And this is the way that you create Siesta file. And remember to look into my GitHub repository, in which I have mentioned all the utilities and the tutorials over here. These are the tutorials that you can refer for the creating input file and to know each and every parameter for this. And you can refer the input files, FTF files that I have created over here to specify in the input file. Okay. So after a successful run, the next tutorial I'm going to show you how to create a band structure plot and DOS plot using GNU plot program. Thanks. Hello people, welcome to my channel Informatics. In the last video I have shown you how to run Siesta calculations, and today I am going to show you how to analyze the output, some of the tricks, how to depict the output from the Siesta calculation, and hope you like it. And please like, comment, share and subscribe to my channel, and comment below what would be the next video that you want, on which topic do you want me to do next tutorial. Please comment below. Thanks. So let's get started. So in the previous video I have run a Siesta calculations, and here are the outputs that is produced from a single Siesta run. And the most important file that you want to analyze is the out file, which is produced from a Siesta run. And the most important part of the Siesta, the out file, the result file, will be this one. You'll be mostly concentrating on total energy, free energy, and also on the relaxed atomic coordinates, etc., and unit cell vectors, etc. There are so many options that is dependent on your specific choice what you want to analyze from a DFT run. And rather than opening the out file and analyzing manually, I can show you one of the tool which is provided by Siesta Util command. In the util folder you have this cml-comp, and you have this ccwidge tool which can convert the XML file produced from the Siesta run to XHTML, which you can open in a web browser. So I will show you how to do that. So the command is ccwidge bulk.xml, the file that has been produced by the Siesta run, and that's it. Press enter. So there will be a file called bulk.xhtml, you can see here, and if you open it, it opens in a web browser. where you can see the metadata, how the Siesta run has been performed, your input parameters, and the initial system of your crystal structure, and the body of the simulation, how many steps it has taken to reach a convergence. And this is your final system, which you can get all the final energy, total energy, free energy, etc. And here is the final output structure uh, that you can directly analyze from here. And here are some of the summary informations. So this is one of the convenient way to convert a big calculation also to a web browser format, that you can share it, and you don't have to bother about the space that is required to send all the files in email also. So you can send this file and they can analyze the output from this access table format. So another way of analyzing the output is by using Unix commands. So this is your result.out file, and you need specific outputs to be analyzed, such as if you want this final energy column to analyze from the output, you don't have to open it manually, rather you have to use the grep command that I'm going to show you. So what would be the grep command is grep -a. How many lines? A means after. So how many lines do you need from that particular string? Suppose you need 10 lines, and you paste the string that you want to analyze within the double quotes and your file. Here it is. You get the same output as here. Like in here, you can see the output: final energy, band structure, kinetic, etc. So suppose if you need this cell volume column, then what you can do is just paste that cell volume thing, and you want only one line after that. So the final cell volume will be this one, and these are the cell volumes that has been, I think, calculated from every CG run, and this is your final volume that you obtain from a converged calculations. So like that, if you make a executable file and run it like this, so you can get all the outputs in a one go. Suppose I have created this file, and to create a Unix sh file, you have to put this command hash !, bin and bash, and all your strings, all your commands to analyze the output. So I'm going to run this, and then you can see how the outputs come over here. So I can show you that. So this is the file. So after writing in Unix commands, what you have to do is you want it to be executable. So +x siesta out.sh. So what you can do is siesta out.sh result.audio file name, and yes, you get all the outputs from here. Like the final energy I need the stress tensors, I need the cell volume, I need the number of atoms, like what I have been specified in the output file, in the input file, sorry. So it's like number of atoms. Here you get the number of atoms, you get final energy, block of lattice vectors, yes, block of lattice vectors, and cell volume, the final cell volume. So this is the way to analyze each and every output very more conveniently without opening the result.output manually and look into each and every column that you want to analyze. So this is one of the tricks. I think you have many other tricks to analyze all the outputs, but this is the way that I do, and it is much more convenient for me. So thank you. Hello everyone, welcome to my channel Informatics. After uploading all the videos, I got a request from one of my friend to describe the Siesta output files produced by a single DFT calculation run. And today I'm going to show you what are the files produced by the Siesta and what they mean actually. So let's get started. So this is one of the Siesta run, and I'm going to explain you what are these files produced by a single electronic structure calculation. And so first of all, this one, a normal exit that gives you a description about your run, that your run has been successfully completed. These two files produced by one single calculation gives you the Harris energy. Both are same. If you can check, both contains the same energies. This is about the bulk allocation memory, in which how many if you do a MPI calculation, how many nodes has been allocated to run your calculation. This is the file which is used for the animation, which you can visualize by using Molden software. So this is the animation file, and this file bulk.bands is the bands file which is used to plot the band structure. These two files are the description of the bonds, in which you can see that these are the bonds at your, this is one of the example that I have been doing, and these are the bonds that is between the atoms, as you can see. And this is also the same file produced, and this file CG is the coordinate optimization by conjugate gradient file, which records all the steps that is run by a single DFT calculation, and these are the CZ atomic coordinates. .dm file is the initial density matrix file, which is used to restart a calculation. You need this file to restart a calculation if something happens, or power failure or something. Then you can use this file to restart your calculation, or also you can use this to run a new calculation based upon your previous output. So this is DRHO file, which is the valence pseudocharge density file. It contains the density of the valence pseudocharge. This is the eigenvalue file, which is used to plot the density of states, or DOS plot. And this is the file which contains all the forces. .fa means forces, and WFSX and HSX, these are the two files which are produced if you turn on the tag of a wave function file. These are both wave function file which can be used to plot the wave function. IOCH file is the ionic charge file. I can show you in the input file where all these options has been mentioned, and how these outputs have been generated. So when you see this, if these options are turned on or set to true, these files are produced. WFSX, HSX, IOCH, and TOCH, and these are all the charge densities and potentials for the microwave. And wave function of bands, these are the wave function files which I have shown you. And these are the options for the MD options. If you turn on the tag of MD molecular dynamics over here, then you have these many files produced, and out of all these files, this file is really important to check the energy, how your calculation has been converged, from what energy it has started and what energy does it end, and how many steps has been taken to reach the convergence. This is the volume, this is the pressure, this is the total energy, this is the Kohn-Sham energy. So you can analyze on the basis of that. MDCAR gives you all the coordinates that has been run through your CG calculation, and this is your initial coordinate that you have given, and this is your final coordinates that you can get out of a single DFT calculation. This file is the orbital index file, which is I think which is this is not important for for any analysis or something. This is the row file which instructs to write the valence pseudo charge density at the mesh cutoff that you have been used, and this file can be used for the next iteration, for the starting a new calculation. And this is the final atomic coordinates which has been written over here, and these are the lattice vector points, and these are the atomic coordinates which is in fractional format. The times is which program takes how much time. You can see that from your calculation, if you have a big calculation, how much time it has been taken for writing each and every file that you can see in this. I mean, this is for the computer professionals, those who have been working with parallel programming or anything related to software information, so which is not required for the physicists. This is the XML file which I have shown you how to convert the XML file to XHTML by using CCVich, and which is a very convenient way to read your output rather than opening your result.out file. .xv file contains positions and the velocities of your calculation. .xyz format contains all the coordinates which you can visualize by using the software called Vesta. And grid NC files, all the grid .nc files are the files which are produced if your net CDF option is on. You can read it in the manual regarding this grid NC, which is used for, I think, for charge density plots and for further analysis, you can see. And this is the log file, which is most important. If you open it, then you have many options that has been written, and you can see that after turning on the tag in your input file, how the tags have been generated and what are the default tags that have been used, and you can change accordingly to your convenience, and you can produce your results based upon your input file by using this FTF log file. In my case, I think this is the most important file, not only in the Siesta software but also in all the free software. You have this log file that you can see to change your input accordingly. And you have ion files, two ion files. In my case, I'm using zinc oxide, so oxygen.ion and zinc.ion files are produced, in which Rather than if you don't have any PSF format, generally Siesta accepts all the PSF format pseudo-potentials. If you don't have any access to PSF pseudo-potentials, you can use these o.ion files in your calculation by turning on the tag named as, I can show you here, user basis to true, and you can copy .ion files and run it in a separate calculation. I can show you one example how this calculation can be run. So I have to copy this, relax FDF, and that's it. So I'm just turning off this tag for now, so that you can understand the difference, why these ion files are important. And I'm going to run this calculation, Siesta relax.ftf. As you can see, your calculation cannot run because you have not used this tag. So if you turn on this tag, like somewhere over here, user basis to true. So if you run the command again, yes, it starts running. So you need these ion files to if you don't have any access to the PSF format of pseudo-potentials, you can use these ion files and use the tag user basis to true. Then you can run your calculation according to your choice. And okay, I'm going to stop this. So these are the files which are produced, and I hope this information is useful, as yesterday one of my colleagues suggested to explain each and every file. So that's why I'm making this tutorial for you, and hope you like it. Thanks. Hello people, welcome to my channel Informatics. Today I'm going to show you a convenient way to analyze the output of your DFT calculation, that how many CG cycle has been performed to get a convergence criteria out of your calculation. And this is a bash script which has been provided by a company called Simmune Atomistics, and this is a commercial company. They also provide basis sets for all the elements, and also Siesta codes that you can subscribe for, and you can contact them if you want a commercial version of the software. So one of the scripts that they have provided, I'm going to show you how they have analyzed each CG cycle, which is called the analysis of electron density convergence, to plot each CG cycle that has been performed in your calculation. So let's get started. So this is one of the DFT calculation that have been performed as shown in my previous videos, and this is the script that they have provided to individually plot each CG cycle, and to get the outputs of each CG cycle that has been performed in your calculation. I'm going to execute this, and I can show you that how individual CG cycle can be generated. So what you have to do is open the command line and save this script in .sh format, and just type scf cycle.sh to get it executed. So the command would be scf cycle.sh and your result dot out file, and that's it. You the automatically all the CG cycle that has been performed in your calculation can be generated, and you can see how the energy has been converged from the first point to the last point of your convergence criteria. So this is the way that you create all your CG cycles. And to plot individual CG cycle, they have provided a GNU script in which you can plot the electron density variation, free energy, Kohn-Sham energy, and Harris energy that you generally get in your output file. That I can show you where you can where you get this output. Yeah, this one. So this is the one self-consistent field in which you have 1, 2, 3, 4 columns that you can plot for each CG cycle that has been performed in your calculation. So to plot this, they created another script called which I will provide in my description in the video. So to execute this, what you have to do is plot scf.sh and one of your CG cycle that you want. So I'm going with the first one, CG cycle 1 dot text, and that's it. You get a nice GNU plot in which you have this electronic density variation, free energy, Kohn-Sham energy, and Harris energy. Also, you can perform the same with all the other cycles that have been performed. So maybe I will go to name it as Convergence SCF first cycle. So you want to plot for the 10th cycle, and yes, you get the plot out of it, and you can see that how you can compare the two plots, that how your first CG cycle and this one is your last CG cycle, how the energy has been converged, and you compare the values out of it, and you get all the outputs that you ran from a DFT calculation. You can visualize it by using these two scripts, and more conveniently you can analyze all the outputs that can be performed, and also it will be helpful for publication, I guess. So that's it, and hope to see you in the next video with some more tutorials on Siesta. And thanks. Please like, comment, and subscribe to my channel, and please tell me what would be my next topic so that I can make another tutorial on that. Thanks. Hello everyone, welcome to my channel Informatics. Today I'm going to show you how to create a band structure file from a Siesta run and how to plot it by using GNU plot, as well as I'm also going to show you how to plot DOS plot and how to create a DOS file from a Siesta calculation. So let's get started. So this is the output that I got from a single Siesta calculation run, and the files which are required for the band structure analysis and DOS plot are bulk.bands and bulk.eig. EIG file is nothing but the eigen file which is generated from Siesta output in Siesta calculation, and to generate the bulk.bands you have to specify the band structure analysis tag in the input file, and these coordinates and your Brilliant zone points can be obtained from crystallographic server, in which you have to go for the space groups and you have to select which in which space group your material belongs to. I'm going to show you an example. If suppose you are going for P3212 space group, and you have to go to this k vector types of space group, in which you have to mention the number in which this space group belong to, and press enter, and you get all the coordinates over here, and these are the k vector descriptions. So in my example, I'm going to show you P63MC, which is 186, P63MC 186, and these are the k point descriptions, and these are the coordinates. The coordinates which I have used in my calculation is like ALM gamma AHK gamma. Suppose for A, my k vector points are 0, 0 and half. As you can see over here, for the A is 0, 0 and half. Like that, you can specify all your bandline scale, and you can produce an output out of it. So I'm going to show you how to create a DAT file out of it from the bulk.bands and plot it using GNU plot. The two utilities which you require to plot the band structure and DOS are ike2dos and new.gnu bands. Now I'm going to show you how to create this DAT file for the GNU plotting. So what you have to do is, you have to enter new.gnu bands. -f is used for Fermi level energy shifting, and your file name to bands.dat. That's it. Your file is produced and your Fermi level energy is shifted to 0. Previously, if you open this, you can find the Fermi level at this point. This is the Fermi level is written on the first line of this bulk.bands, and also the band line scale that you have mentioned in your FTF file is written over here, and these are the coordinates in which these lines have been placed. So which I'm going to show you in the GNU plot description how these things work. So now you have created the bands.dat plot. Now for the DOS plot, you have to input ike2dos to convert the eigen file into a DAT file for the DOS plotting. So -s would be for the smearing parameter, Gaussian smearing. Small m would be for the energy range scale. For me, let's say -10. Capital M would be the energy scale which is on the other side, which is, I can specify the maximum scale that I want, 10. And -f would be the Fermi level shift, because in this the Fermi level is written over here on the first line, that is -5.9275, that you have to shift to 0. So for that you have to mention -f and your eigenfile, and which you can plot at dos.dat. So at first I'm going to show you how you plot this dos.dat, in which you can see that when you put the option -f, the Fermi energy has been shifted to 0. So I am using xmgrace to plot the DOS plot, and you can see, as you have mentioned in your options, -s, which is for smearing, you get a smooth smearing out of it, and this is your DOS plot. You can modify it later on for the publication. So this is all about the DOS plot. Now I'm going to show you. So if you use xmgrace for the band structure plot, so it looks a little bit strange in XMGrace, which is kind of messy. But if you use GNU plot, then it is kind of good to have a publication quality figure. So I'm going to show you what are the input commands for GNU plot, which I have created a file in which you can plot your band structure. So this is the file that I have created, in which you have I'm going to keep all these lines in the description so that you can plot it easily. You can copy it and just paste it. So first thing what you have to do is the setting the terminal for the PostScript EPS or PDF or whatever you want, and the output file name, your access properties, and your x minimum and x max. And x minimum and x max can be obtained from this bulk.bands file. You go to the end of the file and you have the range from the x minimum, that is 0.000 to 6.634146. So in this way you can mention the x minimum and x max, and y minimum and y max depends upon your choice, what range do you want, and then you have to fit the x range and y range. And these are the points of high symmetry, in which you have to that can be obtained from this file. As you can see, all the high symmetric points have been written over here, 0.000 8312 until 6.6341. So this is the place where you mention all the high symmetric points, and these are for the high symmetry lines, which you can find in my description. And these are some of the commands to plot the band structure. So you have to save it in the extension .p, so that GNU plot can recognize the .p extension and plot the band structure for you. So for that, I'm going to paste it over here and run it. The command would be GNU plot band.p. That's it, your band structure has been created, and you get a stunning plot out of it, as you can see. So this has been saved in EPS format so that you can edit it and you can send it for the journal, because they generally accept EPS format, which is quite easy to do with the graphical softwares, easy to modify in the graphical software. So this is a plot that can be generated from the GNU plot commands, and you can put colors over here that you can specify later, but this is what generally the plot looks like, and it is quite good. And one more thing I want to tell you, that how to this band gap is one of the concern that is which can be easily obtained using Quantum Espresso or WASP or any other software. But for Siesta, there are no scripts to obtain the band gap. For that, I have modified this my band structure diagram to HOMO and LUMO, in which you can see that for the HOMO level I have mentioned y minimum would be -5 and y maximum would be 0, and all the rest are the same. But one thing I have put it over here is the stats command in the GNU plot, in which you can see all the statistics out of your plot. I'm going to do that, and you can see how this HOMO data has been printed into the, as I have set the command to vbm.dat. So you can see how this has been printed. Suppose GNU plot homo.p, and you can see that this is the homo plot in which the range has been mentioned from -5 to 0. You get the valence band maximum, and here is the stat for this, in which you can see that your maximum y would be -0.2923. So this will be your valence band maximum. In the similar way, you can plot for lumo.p, in which conduction band minimum would be, will be there, and here you can see the minimum y would be 0.27. In this way, you can subtract both of them and to obtain the band gap. And for this lumo, the range would be y minimum would be 0 and y maximum would be 5. So in the plot you can see that the y minimum would be 0 and y maximum, this is the positive side and that is the negative side. That's the difference. That's how you get the band gap out of it. So this is all. I'm going to attach all the scripts in my description and hope you like it. Thanks. Hello people, welcome back to my channel Informatics. Hope you had a good summer, and during summer vacation many people requested me to do the convergence test by using Siesta, by using the bash script or shell script you may call. So I have decided to make a tutorial on the convergence test based upon the k-points, mesh cutoff, and lattice optimization that you can do. I'm going to show you one example for the molecule that I'm working, the material that I'm working, that is zinc oxide. So by using Siesta 4.1 version, I'm going to show you how to converge the lattice, the k-points, and the mesh cutoff, and then how you can run the final calculation by using those converged k-points. So it is quite a difficult task to decide what k-point should we choose for the bulky unit cell, and what mesh cutoff should we choose, because in Siesta you have to explicitly give the lattice, not the lattice, the mesh cutoff and the k-points, as well as many other parameters like DM tolerance, stress tolerance, etc., that I'm going to show you how you can optimize. And you can do the optimization by using your local computer. You don't need a server or a supercomputer to do that, because this is going to be for the unit cell only. Later on, after after getting converged k points and mesh cutoff, you can do surface calculation and many other, whatever the work that you are going to do, that you can perform there. So I'm going to show you how many the scripts that you can utilize for the k points, for the lattice optimization, and the mesh cutoff. So first thing is to do is the lattice optimization script, of course. Where, in my case, I don't need the lattice optimization, because all the lattice vectors for the zinc oxide has already been known, because I got it from experimental value. So I don't need to do this lattice optimization test for zinc oxide. But for other cases, like if you are taking silicon or gold or diamond or something, whatever the material that you have, if you don't know the lattice parameters that is experimentally calculated, then you have to do the lattice optimization. But I will show you the script how to do that. So first of all, let me open the script for the k-point convergence, or the k-point script. And this video has already been taught by Dr. Mohanlal Verma in his tutorial videos, but after getting so many requests, I decided to do it, and I'm going to use the bash script that has been used by Dr. Mohanlal Verma for the optimization purpose. So let's get started. So this is the keypoint script, in which what you have to do is, first you have to make a directory called cont or continue, and you have to give a loop for how many folders you want, how many keypoints do you want for the optimization purpose. Like for in my case, I'm using two let is I mean the keypoint 2 until 14 within a sequence of 1. So the folders that will be created will be 2, 3, 4, 5 until 14. And the continuation folder that you have made, you have to cp for each folder when the calculation is finished for each folder. Like suppose for the second second folder, like the folder number 2, if the process has been completed, then the continuation directory will be copied from the 2 to 3, and then the continuation of the Siesta calculations will be done. So this will be the CDI means $I means the I which you have given for the loop. It will loop in each directory. And also the most important thing is you have to copy all the pseudo-potentials, which I'm going to use is the .psf format, and the executable that you have installed in your local computer, which is, if you are a Mac user, it should be your username, Siesta 4.1, object, and Siesta. Siesta is the executable file that you want to give. And now you need the input file for that, and the command would be cat followed by a greater than or greater than symbol, and your ftf script, and starting with EOF, and you have your input file over here. In this case, what you have to do is all the parameters should be the same, but the only thing that you want to change is that you want to put is $I over here, $I over here, and $I over here, because you are going to loop it, and because you have given the for the I instance. So if you write here something for J, for A, for B, for C, or something like that, so you have to specify that suppose you have given for A in sec minus W2 114, then you have to give $A, $A, something like that. You have to give the the loop over here, and all the parameters that I have already explained in my previous videos. You have to see you have to follow those videos to see how the input file has been created by using for the Siesta purpose, and the commands will be the same. And the last line would be the EOF, because here you have initiated the input file. You have to close it, and your command to run the Siesta program, then again cd dot dot, and you don't need the continuation file, so you have to remove it, and again make directory continue for the next one, and like that. If you want your density matrix file to be copied to the next directory, then you can use this command, or otherwise hash it, or something like that you could do. And at last it should be done. So this will be the script for the keypoint optimization. So I'm going to test run for this keypoint script. And remember one thing, you have to the folder in which you are running the script, you have to keep the pseudo-potentials in that directory, and then run it from that directory only. Suppose and also you want to make your sh or the bash script executable, so you have to give the command like chmod plus x keypoint sh, and then followed by the command / keypoint script.sh. So in this way the folders will be created. As I have mentioned, the continuation folder will be generated in each step, and here is your Siesta that has been running. So in this way you can initiate the convergence test for the k-point optimization like this. So once you get your k-point, I'm going to terminate this program. Once you get your k-point, and you have to see the convergence where it is getting converged finally. So you will get a parabola or something, a graph in which your convergence will be given in the graph. Then you can start from that point where it is getting converged and use those k points for the next script. So I'm not going to use the lattice optimization script because my lattice has been already known. But in this case, in the lattice optimization, the script will be the same, but what you have to change is you have to mention the k points, because as you get the converged k points from your first script, then you have to mention your k points. And in the lattice vectors, you have to specify, if suppose you don't know this one, so you can initiate it from suppose your first a lattice vector is something like 3 point, suppose the experimental lattice vector is 3.3 or 3.4 or something like that. You don't know at all, but you need to optimize that. So you can initiate the sequence from 3.1 and starting with, if you are suppose 0.5 until if you need until 7 or something, or something like 4.5. Sorry, it should be, so if you are making it 0.1 until 4.0, yes, then each folder will be created like this. So what you have to give is on the first a lattice vector, instead of giving the value, you have to put $I over here, and that's it. And you can run the script as it is, but you have to give the k points that has been converged in your first k point optimization script. Those who don't know the lattice constants or the lattice vectors, they have to run the lattice optimization script first, and then the k points, and then you can proceed for the mesh cutoff parameters. So this is the way that you can optimize and converge, and you can see the graph. I can show you one of the graphs that I have generated, and how you can decide what k point should you choose, what mesh cutoff, and what other parameters you can choose. So the next script will be the mesh cutoff, in which you have mentioned your lattice vectors, your k points. Key points, if you have mentioned, if you have got your converged key points. I'm just going to, and then when you go for the mesh cutoff over executing the mesh cutoff, what you can do is you have given your k points. So I was looking for the k point graph, and I have got it for my calculation, and I'm going to show you after optimizing the k points how you come to know that what k point should we use for the convergence. And this should be the graph. I can show you. Yeah, this should be the graph that has been converged in my calculation by using Siesta PSF Pseudo-potentials. These are the LDA calculations. So this will be the k point cutoff, and I have given the folder from 2 to 14, I guess. Yes, 2 to 14. So the folders will be 2, 3, 4, 5, 6 until the 14. Until 14. And at the first step, in the second folder, you have your Siesta run from 2 to 14, and you can see that at the point around 4 or 5, my energy is getting converged, and I think for my calculation I can use the starting point at which the energy has been getting converged. So I can use either 4 or 5 k points. As you can see, you can see that the line is straight, so I can use 5 the k points for my calculations. So in this case, what you can do is you can use 5 and 5 for your unit cell calculation for the mesh cutoff script optimization. And in the mesh cutoff, what you have to give is explicitly you have to give the $I symbol. So in this case, my mesh cutoff starts from 50 with a difference of 50 until 500. So you get a curve in which also you can find the the similar energies, and you can point out where your energy is getting converged, and you can use that mesh cutoff energy for your rest of your calculations. The similar way you can use for the lattice optimization also. The similar way you can use, I'm going to show you some of the other parameters that you can optimize. Suppose for example this MD max force tolerance, mixing weight, and also there is another parameter called pulley forces. Yes, DM number of pulley also you can optimize by using the same script, by just putting the $I symbol and giving rest of the parameters for the calculations. So pulley forces are important because in my previous videos I have shown you some of the trans-Siesta calculations in which this pulley forces comes into play. It has an important role, and also these pulley forces can be used for different types of calculations like high pressure calculations, etc. So you need to optimize these pulley forces also. This is only for the Siesta users, not for the, because it in VASP I think the pulley has been defined optionally, or what you can defined in default. You don't have to give any explicit pulley options over there, but in Siesta you have to give each and every pattern. Also you can comment out these pulley forces also, because if you don't know anything about any of the parameters whatever you are using, you just comment on it, it can use the default one. But I would recommend everyone to read the manual, and I suggest everyone to use each and every parameter, just play around by using your unit cell only, and optimize by using energy. And once you get the optimized parameters, then you can start your calculation for different types of applications like surface calculations or trans-Siesta calculations, etc., etc. So it is a good approach to know each and every parameter and to use the optimal parameters by getting the energies, getting the forces, lattice constants, mesh cutoff, k points, etc., so that you can use for the later purpose. So in this way you can optimize everything, get the energies, and plot it, and visually see where the energy has been converged. These are the absolute energies. So this is the only parameter that you can decide during the convergence test. These are the absolute energies, and you can decide from those absolute energies. But also you can see the forces, your lattice parameters, how they have been changing, and you can do a lot of things. But this is a good starting point in which you can start your calculations. So once getting all the parameters, as usual you can run your Siesta program. And thanks for 100 subscribers, reaching 100 subscribers, and hope I would get more subscribers as well as more share, comment, and likes. Thank you very much. And I will see you in my next video. One of my subscriber requested me to do a video on nanotube calculations by using carbon nanotube, and tomorrow I'm going to show you how to generate carbon nanotubes by using one software which is I think for Windows, and I'll see you tomorrow. Thanks. Hello everyone, welcome back to my channel. I hope you have enjoyed my latest updates on my YouTube channel related to Tron Siesta and Siesta calculations. This particular video is concerned about uh, hybrid functionals in Siesta, and also how to use electric field parameter in FDF file in Siesta, and how to perform the calculations. This is a particular request from one of my old friend from Facebook, and based on his request, I decided to make this video on hybrid potentials, and also on electric field calculations, how to perform, how to utilize the parameter of electric field in FDF file, and you do the calculations. So I hope you will enjoy this, and thank you very much. Let's begin. So if you go to the Siesta manual 4.1.b4 version, and you find the search term called correlation, and you will find this extends correlation functionals, go to this particular section 6.6, and you will find different types of functionals, different types of authors, and there are three types of functionals, which is number one is local density approximation. Another one is GGA, generalized gradient approximation, and VDW, which is related to van der Waals. And these are the extends correlation functional authors, in which you find a variety of authors in here. And if you go to the particular section called XC extends correlation.hybrid, you will find how to use this cocktail of functionals, how to mix these functionals and authors in a particular order, and this parameter can be utilized in the FDF file. In this example, they have done 75 to 25% mixture of CA and PBE correlation with LDA as a functional, GG as a functional, and correlation as CA and PBE as another correlation. So in here, you can see they have used 75 to 25 mixture of LDA and GGA. This 0.5 and 0.5 is nothing but they have used two potentials. I mean, yeah, they have divided 50% of it, 50% of exchange functional will be used by LDA, 50% will be used by GGA. And if you consider the correlation, the CA will be used 75% and PBE will be used 25%. In that particular sense, you can define this block in the FDF file, and you can run the calculations. Fortunately, I have done one calculation based on these parameters, and I found a difference in total energy, and also in different different output values of Siesta calculations. So I'm going to show you how I have performed this calculation and where to define this particular functional. And another update is if you want to use electric field in your calculation. Okay, let me see. Yeah, if you want to use electric field in your calculation, then there is a section that you can define in your FDF file. In this example, in this particular example, what they have done is they have defined some voltage per angstrom in Z direction. In the similar way, you can use the same in Y direction and X direction as well. So you just have to define this particular parameter in your FTF file, and your calculation will run based on these parameters. So I have done that particular calculation also. I'm going to show you how this affects your calculation and how you can effectively utilize this electric field parameter in your FTF file. So let me go to my account. Okay, so here, one particular, uh, um, uh, not particular, I would say if you consider these type of hybrid functional calculations, so you need to carefully define your pseudopotentials, since you are using the cocktail of functionals, cocktail of pseudopotentials in here. So you need to define carefully these pseudopotentials that is available over here. If you go to this particular site, which is cornell.edu, I think the website has been shut down for a period of time, but now they have opened it. And here you can find all types of GGA and LDA potentials. And the particular file which is going to be used by Siesta is .psf. So you will find, suppose, for example, if you take hydrogen, so h.psf will correlate to LDA, and XC authors will be PZ. So in that case, if you use GGA, then the exchange will be GGA and correlation will be PPE. So likewise, you can download all these potentials, and you can define this potential in your FTF file. I'm going to show you how to define those potentials. So I'm going to open one FTF file. So let me copy this and open in a bigger text file. I would say, if you close this. Yeah. So if you go here, all the parameters are defined, in the similar way that you define in your normal FTF files. But if you consider over here, number of species, I have changed it because this is a calculation related to only silicon, I guess. Yes, silicon. This is a slab calculation, 2D material, silicon. So I have only, there is only one chemical species over here, that is silicon. So if you see over here, I have used a number of species as 2, but I have used only silicon in this particular calculations. So what I have done, okay, I'm going to show you another FTF file in which normal calculation has been done. So this is a normal calculation, as you can see. So number of species is 1, number of atoms is 32, and there is only one type of material over here, that is silicon, Si. So this is a normal calculation that you regularly perform in your Siesta calculation. So if you have downloaded something called si.psf, then you define that particular pseudopotential over here. So the name has to be similar, otherwise the calculation won't run. So if you define your PSF as I have defined over here, si gga.psf over here, I have to define this system, this chemical species level as si gga, so that your calculation will run. If you define your pseudopotential file as si, then you have to define the same over here, si. Otherwise, your calculation will stop. So be careful with that particular chemical species label, and your calculation will run fine. This is the normal Siesta calculation. So if you want to use 2 different potentials, so I have downloaded 2 different potentials and of that particular element, which is silicon in this case. One is GGA, one is LDA. So I have defined GGA potential
as I have renamed it, of course, sigga.psf, and over here silda.psf. So if you go to the postcard file, you can see the same particular element I have defined number of species as 2, and I have defined two chemical species block. One is sigga and another one is silda with the same atomic number. So everything will be same, just you have to mix these functionals with the same element name. This is the only modifications that you have to do. And the next thing that you have to do is you have to define this particular block, hybrid block, as I have shown you in the Siesta manual. You have to define this particular block, xc.hybrid, and the potentials that you are going to use are two. One is LDACA, which is I'm using over here 75%, GGAPB 25%. So you can also change this to 50%, 50% as per your wish, and you can define this hybrid pseudo-potentials over here in this manner. So be careful with this particular format, otherwise your calculation won't run. So I have run one calculation, and if you go for the out file, okay, let me copy this. Yeah, if you copy this, as you can see over here, yeah, I have defined these two chemical species label, and this is the cocktail of functional, the hybrid functionals. And you can see there will be a block, there will be a section in which this will be defined after the end of your input file. So where the actual Siesta calculation starts. So it will automatically recognize that we are using hybrid exchange correlation functional, and the functional that we are using is LDA. Another one is GGA. Authors are CA and PBE, and the weights are 0.5, 0.5 in both functional cases. And the weights for the authors are the correlation, exchange correlation is 75% and 25%. In this way, you have to define the hybrid functional in your calculations. And remember, this particular section, that the same element can be defined twice with using two potentials. If you define three potentials, then you have to input another block over here. So if you go over here, then you have to input 3, then again 14, then of course if you want to use VDW potentials, so define a VDW, and also a number of species has to be changed to 3. The same element, but different types of potentials you define in the XC hybrid block. So if you want to use another one, suppose VDW, and you go to the manual and check for what are the authors that is available in VDW. I think the most updated one is, I think this one, yes, DRSLL, I guess, yes, this one, because I have been using a lot this particular functional. So you can define this DRSLL over here. So if you go here, yeah, DRSLL, and the weights can be distributed as 0.3, 0.3, and 0.3. So I'll be using another 33 over here, 33, or maybe 0.33. So like that, you can define your potentials. So remember this particular section block of chemical species label, otherwise your calculation will stop. So as you can see in the output file, there are hybrid exchange correlation functionals has been defined, which has been taken by this Siesta output file. And you see there are different types of pseudo-potentials that has been used. One is from a GGA potential, and another one is from LDA potentials. So it has used both of them. And if you go down, Okay, I just want to show you that how the energy differs. The calculation has been done, and if you go over here to the sorry, the final energy over here, where is that? I think this one, yes, this one, or maybe you consider the total energy. Yeah, E total over here. If you consider this, as you can see, it has minus 3403.895155. This is the total energy of this particular hybrid functional calculation. And if you go for the calculation, which I've run only using GGA potential, and if you see the relax under, so if you can see my FTF file, I have used only GGA potential over here, and a number of species block, I have set it to 1. So if you go to relax_relax.out file, and as you can see, the energy will differ. Yeah, as you can see here, the total energy is 3390, but here in functional, you can see 3380. So a little bit of difference in energy has been pointed out over here. So I think this is the way that this hybrid functional works. I don't know exactly how accurate is this, but I figured out that this is the way to use this hybrid functional in Siesta calculations. And also you can see some of the parameters over here. If you compare these two parameters, so the final energy is 1207 by using only GGA, and you can see minus 1190 over here. Yeah, and this is a band structure energy, I think in electron volts. And you go to the total energy, this is minus 3403 in hybrid functionals and 3390 in only GGA functional. So this is the way how you introduce hybrid functionals into your calculations. Remember to exactly use the name of the PSF file. If you are using the same element, remember to use this exact name of this PSF file in 2 sections and define the exact name in your FTF file. Go FTF file, SIGGA, as you can see, SIGGA, here SIGGA, and here SILDA, over here SILDA. So everything will be same, just you have to concentrate, focus on the name, and also define, if you are using hybrid functional, define the number of species as 2. And this is the way that you do hybrid functional calculations. And the next update is regarding this electric field. I have shown you, if we go for electric field, yes, and you see this is the block that you have to define in your input file. So I have defined the same in my input file, postcard.ftf. Go. So let me copy it. So this is the best text editor also, I would say, Sublime, which is available in Mac. Those who are having Mac, they can use this. I mean, it's very handy to use and it has some excellent features. So over here, as you can see, I have used only GGA potential. And if you go down, I have defined the block of external electric field in this calculation. So in my previous calculation, I have calculated only by using GGA, and this one I have used electric field in Y direction because I have to observe the molecules from Y direction, and all the calculation, the scattering region or in the transistor calculations, I have done from the Y direction as well. So I have defined this external field in Y direction, that is 0.5 volts per angstrom. And if you can see the output file, okay, let me show you this GGA output file, in which I have not defined anything. And you can see the total energy and this particular section, electrical dipole. As you can see, this is uh, nothing but 0 in this case, and the total energy might differ in this case. So if you go to the electric field calculation and open the relax_out file, okay, let me copy this. So if you see over here, in a normal calculation, if you do, your electric field dipole is almost 0 in this case. But if you define the electric field in your uh, uh, FTF file, so you will see that I have defined my electric field from the y direction, right? So I got the values over here, as you can see. So this is 0, x direction I have not defined, z direction I have not defined, so it is equivalent to 0. But in the y direction, I have defined this particular section, and also the particular energy over here, 3365, and here the energy is a little bit a difference, but almost similar. The only change in the output file will be in the electrical dipole section. So this is how you can introduce electric field in your FTF file and do your calculations. And I think, yeah, this much. So be sure for the hybrid functionals, be sure to uh, name it perfectly and define it perfectly in your FTF file, and your calculation will go fine. So see you next time. Thank you.
Hello people, welcome back to my channel Informatics. Today we'll discuss about the Phonon calculations in Siesta, how to efficiently do a Phonon calculation in Siesta, as well as to produce a Phonon band structure. So for this you need three things. One is FC build, the next one is the Vibra tool, which you can find it in the Siesta source directory in the utils folder. That I will show you how to build those tools, as well as how to use those tools to produce the force constant matrix which is required for the Phonon band structure, as well as how to run the force constant matrix as an input for the Vibra tool to calculate the Phonon band structure. So for this, another important thing is you need a large supercell to calculate the Phonon band structure. You cannot do it for the unit cell. You won't get the band structure exactly matching to the experimental values. For that, you need a large supercells. And the most crucial information that has been written into the file called FC file, the system level.fc file, which consists of all the force constant matrix. It's a dynamical matrix. So that's it. Let's get started. Thanks. So to start a Phonon calculation in Siesta particularly, you can refer the manual. I think this is 4.1.b4 version, in which you go to the section 7.8 and you have the Phonon calculations parameters that you can define. So one of the important parameters that you need to define is MD type of run, which is FC. FC is used for the Phonon calculation. So this compute force constants matrix for Phonon calculation. So you need to explicitly define FC in the section of MD type of run. Rather than CZ, you define FC for the force constants matrix calculations. Okay, so you need specific files. I'm going to show you one example of zinc oxide, since I'm working on that. So first of all, you need the pseudo-potential file, which is in PSF format, and which you can also refer from my previous tutorial how to build the pseudo-potentials for specific elements. that you can refer and build your pseudo-potentials accordingly. So for this I have taken zinc oxide. So I have taken the zinc pseudo-potential file and oxygen pseudo-potential file, which is in PSF format, and three tools that you require for the Phonon calculation. One is FC build, another one is GNU bands, and another one is the Vibra. This FC build is used to create an FTF file for the Phonon calculation. Vibra is to calculate the eigenvectors uh, from the previously built the FC constant matrix. So this tool is used to create the band structure as well. And GNU bands is used to plot the band structure to visualize by using XMGRIS or GNU plot. So I'm going to show you now the architecture of the FTF file that is required for the FC build to create the input for the Phonon calculation. So basically the FTF file consists of system name, you need to define something, system level, you need to define according to your calculations. So I have taken the unit cell for this, which consists of 4 atoms, and the block the lattice vectors, atomic coordinate format, in which I have taken the scaled Cartesians, and also you can also find what are the inputs, in which format the atomic coordinates are in your FTF file. You can define that atomic coordinates format. And next is the block of the atomic coordinates with element numbers as well as the atomic mass of each element. Without this atomic mass you cannot do a Phonon calculations. If you do not input this atomic mass in your atomic coordinate block, the FC calculations won't run. So you have to explicitly define this atomic mass. Okay, and the next thing is for the Phonon calculations, it is the most important factor to do a Phonon calculation is not in the unit cell but rather in the supercell. So when the supercell is larger, your Phonon calculations will be better. And the other important parameter for this is you don't have to define the k points or the Monco-spec, because this has to run in gamma point only. So this is gamma Phonon calculations only, and this is the default atomic displacement that is defined is 0.04 Bohr, but you can define as per your need. And the another most important parameter is the band line scale. You need to define the band structure. Okay, and the other parameter is the eigenvectors. You want to write the eigenvectors, which you have to set it as true to be able to write the eigenvectors in a specific file. Okay, so this is the Phonon FTF format to be input through FC build to create the fc.ftf file to run the Phonon calculation to generate the force constants matrix file. Okay, so these are the important parameters. So now what you can do is you can get this FC build Vibra from the Siesta Utils directory in the folder named Vibra, and then you go to the terminal. The first command that you want to input here is /fc build and your FTF file, phonon.ftf. Okay, so your output has been written to fc.ftf file. Okay, so this tool is used to create the fc.ftf file. So I'm going to show you how it has been created. So this is your fc.ftf file. Remember, you have mentioned the supercell 1 into 1 into 1 size, so that's why you have 108 atoms. So it is automatically taken into account, so you need not to worry about the atomic coordinates and how many atoms has been generated. So this is the automated tool. Okay, so the next thing is you have all your formats, and it also defines the MD type of run as FC and randomly chosen atom numbers to calculate the force constant matrix. Okay, so this is what the FC build tool has been used to create the fc.ftf file. Now you need another ftf file in which you have to define this fc.ftf file inside that file. So you have to calculate now the normal Siesta calculations, in which you define system name, system level, number of species, and a block of chemical species, basis size. Yeah, you need to define the mesh cutoff and mixing weight, number of Poulet, DM tolerance, whatever the parameters that you need, you can also define that, and include one statement which is percentage include fc.ftf. So this fc.ftf that has been built by using the tool fc.build can be input into this ftf file that you have created manually, not by automatically it has been created. So you have to explicitly define this manually and include this statement percentage include fc.ftf. And remember also this phonon.ftf, your system name and system level, both that you have defined in the phonon.ftf, you need to define the same in the normal Siesta calculations. So the next thing what you need is so you need to run this siesta.ftf by the command siesta.ftf #te phonon.out. Okay, so this will run your fc step has been begun. So it reads the fc.ftf inside this ftf file and it runs the fc steps. Okay, so I'm not going to do it because it will take so much time. So I have been running that calculations since from half an hour. I think it's still running. Okay, so in this way you calculate the Phonon calculations, and it will generate a file which is named as .fc. Yeah, see, .fc, which consists of, after the successful calculation, it will create a .fc file which consists of force constants matrix and atoms displacement. Okay, so this is the force constant matrix that has been created by running the normal Siesta calculations. Okay, so the next thing what you want to do is you need the tool called Vibra, in which you need to define the phonon.ftf file that you have previously mentioned. Okay, where is that? Yeah, this one, phonon.ftf file that you have previously built it, which is required by fc build to create the fc.ftf. so you need to use this file to calculate the eigenvectors. Okay, so for that you need ./vibra and your file. So since I have calculated here, I can input the same input file over here to okay, this is phonon.ftf. Okay, now an eigen value file has been created over here. You can see, which is called ZNO vectors, and also you find the bands, ZNO.bands over here. So now what you can do is you by using GNU bands, you can shift the Fermi level by specifying the command GNU bands -f ZNO.bands and your bands.deft. Okay, oh, sorry, ./GNU bands -f ZNO bands. So you created the bands.dat file, and which you can visualize by using xmgrace bands.dat. Sorry. Simulants. Stop that. Okay, so this is how you create the Phonon band structure. Phonon band structure by you can also verify your results afterwards. So this is a test example that I'm doing with 1 into 1 into 1 supercell. So if you increase the supercell, you can get very fine band structure which matches to the experimental value, I guess. So this is the way how you can do the Phonon calculations in this. The tutorials and the explanation can be found in the given link below my video, and you can refer those tutorials to understand how this band structure has been created and what the Phonon force constant matrix consists of. Okay, so thank you very much. Hello people, welcome back to my channel Informatics. Pardon me for the long interval of this gap for posting all the videos, because I was busy with all my PhD work, and now I am back. I got a little bit free, and now I am back after reading so many comments on YouTube. Now I have decided, okay, let's make some tutorials on Siesta, because Siesta has been upgraded drastically and there are some new features on Siesta. But first let me introduce you the installation, the problem that you are facing in installing WX Dragon on Linux machine. Today I'm going to show you that, and also there is another toolkit called WASPKit which can create a FTF file for Siesta. So let's get started. Thanks. So let me take you to the website of the WX Dragon, in which you can download the proper executable for for your operating system. So don't download this, because previously I have downloaded, I think, this version for the Apple OS or the Mac, but also you can download it for all other operating systems which is Linux based, which is Ubuntu, SUSE, Debian or CentOS. So for now, and also you can download it for Windows also. So for now, in my cluster there is a CentOS version, so I'm going to download this CentOS version WX Dragon 64-bit binary, which is in a format of BZ2, which is clearly written over here. And how to execute it, you can also see here how to execute and how to create the executable program of WX Dragon, which is to be installed in Linux machine. In my previous videos I have shown you the WX Dragon executable for Mac OS, which is quite simple and easy, because you have a DMG file and then you extract the DMG file and you get your WX Dragon executable. So let me take you to my cluster, in which I have downloaded the WX Dragon BZ2. As per the information, you can do bunzip2 WX Dragon.bz2, or there is another option called bzip2 -dk WX Dragon BZ2. So you press enter and then you get your executable file. Now you have to give permission to open that. So for that you need the command chmod u plus x and your executable WX Dragon, and you can open it by /WX Dragon. Yes, now it's open, WX Dragon. So for an example, I have a random Posca file. I don't know the elements. I mean, this is a random Posca file. So you open the Posca file and you click here. Yes, now the WX Dragon is open. You can visualize it. So as you want the Siesta FTF file from here, what you do is you go to the export, and then you have your Siesta, and then click apply, and you have the Siesta FTF file from a normal Posca file. Okay, It's a chemical species and your atomic coordinates with numbers. Okay, if you want to export it for quantum espresso and you have the same, yes, you can do it. But and also you can, if you want something for, let's try something else, suppose Win2K, yes, you have your file. Okay, and let's try another one, Abinit, you have your file. Export DL poly, yes, you have your file. Okay, so this is the way how you install WX Dragon, by creating an executable and giving permission, and then opening it by using /WX Dragon. And you can also set it in a path where you can define the path of WX Dragon and just type WX Dragon and this window will open. Okay, this is the way how you generate FDF file for Siesta. And okay, some problem. Okay, let it be. Okay, this is the way you create. But one thing you have to remember is WX Dragon creates the Siesta FDF file or any other files only until the atomic coordinates, but not with the parameters and everything. So to create an FDF file with parameters, with the default parameters, there is another tool called WASPKit. You can go to WASPKit and download the WASPKit, and the creating executable for the WASPKit is also fairly simple for Linux and Mac OS, as I'm using these two versions. So you download the WASPKit, and I'm going to show you one example how to create the Postcard FDF file with parameters. So I have the Postcard file, and remember, in the Postcard file you have the name of the element or something, you say as molecule, and you need to explicitly specify all the chemical element names above the chemical element numbers. You know how many atoms are there. For example, calcium, we are having only one atom, oxygen 16, carbon 40, hydrogen 48, fluorine 48, boron 2, something like that. So you have to explicitly give this line in the Postcard file to be able to generate FDF file for Siesta by using WASPKit tool. So, and also you need the kpoints file in which you define your Moncost bag or gamma point or something, and you define your kgrid mesh over here. So these two files are necessary or must be present to be able to produce FDF file from WASPKit tool. So I'm going to show you how to export it. So if you have installed WASPKit, you just type WASPKit and the window, the command terminal will open the WASPKit version. And also to remember that the WASPKit version 0.61 is having that option to create a FDF file for Siesta. I don't think so it is present in 1.0 or something, so you have to, but I never tried with other versions, but this is installed in my cluster, so that is fairly simple and easy. So explicitly this version WASPKit 0.61 is used to create Siesta FDF file. I don't know with the other version, you can check. So in this you have the option called structure toolkits. So you press 3 and enter, and there you have two options. One is Postcard, one is Contcar. You can either give Contcar or you can either give Postcard for that. So now I have the Postcard file, and press 1 and enter, and you have the options for generating many different input files for, I think, Quantum Espresso, yes, and ELK, and here there is an option called Siesta, which will create the FDF file. And also there are many options you can explore later. So you input the value 308, yes. Now your FDF file has been created. Remember, when you use WX Dragon, you get until this portion, until atomic coordinates. But when you use WASP-Git, you have options like all the parameters, all the default parameters from Siesta. So this is pretty good, and you can use this directly for optimization of your structure or relaxation purposes with all the default parameters. But you can also change the parameters as per your need, and this is the way that you create FTF file by using the WASP-Git tool. So I'm going to show you how this will not generate this will generate the FDF file, but without the chemical element names it won't generate uh, the proper FDF file. So I'm going to show you. So let me rename it to postcard 1.fdf, and so I'm going to remove this line, okay, and then I will generate let me try to generate the FDF file for Siesta. So WASP Git number 3, which is structure toolkits, and I have the postcard file, and I need Siesta FDF file. See, the FDF file has been generated, but you see over here you have two things. When you have the chemical element names in the postcard file, you have number of atoms, number of species, and everything. But when you don't have that particular chemical element names, you don't have anything. So be careful with that, and try to explicitly mention the chemical element names in the postcard file. Okay, and I'm going to show you another example. I am going to delete this or rename it something, okay, and then I open WASP-Git number 3, number 1 postcard, and I need for Siesta. See, the error will comes up like the kpoints file doesn't exist. So you have to explicitly give the kpoints file ts, okay, so that you can generate the proper FTF file for Siesta. Okay, that's it for today, and thank you very much. Hello everyone, welcome back to my channel Informatics. I wish you a very happy and prosperous new year, and may this 2020 bring you a lot of excitements in your life, as well as a lot of publication for the researchers. During the winter vacation, I was on holiday, and one of my colleagues has requested me to show a tutorial on installing the Vesta program and how to download the structure from materials project and open in Vesta and do some of the modifications or structural modifications to the structures. So let's get started. Thanks. So for installation of a Vesta program, what you have to do is you have to search like Vesta for Mac or Vesta for Linux or Vesta for Windows, and that will redirect you to the Vesta JP Minerals website, in which you can click, and there are many options for the Windows. This is for Mac OS and this is for Linux. So in my case, I'm using Mac OS, so I'm going to download this vesta.dmg file, which I have downloaded already, and just install it as usual, and follow the instructions to install the Vesta program. Okay, so I have already installed the Vesta program. So in this way you can download from this site, and you can install the Vesta program as usual. Okay, so now the next thing is downloading the structure from the materials project is very simple, in which you have to go to this tab, in which it contains so many options. where it contains the batteries options. You can explore all the batteries, explore the materials. These are the crystal toolkit, and explore some of the molecules. You have 4 options. Okay. Generally, people use materials project, I think, for materials and for the batteries. Suppose we go to these materials and click buy elements, then you have the option to select all the elements. In this case, I have selected MO and S. I think you all know the structure is MOS2. Okay, so it will show a lot of various structures in different space groups. So of your particular interest, you can download the structure by clicking one of the display one of the displayed outputs from the from this search, and you can go to that, and you can download the CIF file from this. Either you can download the computed one, in which the materials project has calculated already by using some functional. It is given in the help guides. Okay, or you can use primitive cell or conventional standard. Okay, it depends upon you what you want to do. The other option is you can go to here, also the same thing, you can download from here. And there is another option in which you can download the WASP file format, which are the postcard, or the CIF file format for the AAC to know to modulate the structures. And this is the WASP file format. Okay, you can download all these files from here. Suppose I want to download the postcard file, so you just click download, and the postcard has been downloaded. And you want to open this in Vesta program. So what you have to do is you have to go to the Vesta program. Okay, just drag and drop this postcard file. I think this is error, because in the postcard file, so suppose if you want to open a postcard file in Vesta, what you have to do is you have to mention, oh, these are the direct coordinates. I think this should open, I guess, but why it is not opening, I don't know. It should open actually. Postcard file type is not supported. So for that, what you have to do is you have to just rename the file to postcard.wasp. That's it. Okay, now you click and drag and drop in the Vesta file, and your file will be open. So in this way you can open any postcard format by renaming it to .wasp, and you can open in the Vesta program. And what are the other options is you can go to the objects, where you find all the atom names, how it is characterized over here. And you can edit the cell by using edit data phase, and you have the phase over here. You have the unit cell. You can modify your system according to your particular interest. These are the structural parameters. Okay, these three are mostly applicable to modulate or modify your structures according to your needs, according to your project needs. So in this way you can download, and you can use Vesta for many purposes. And the other thing is you can save also in different file formats. For that you need to go to the file, export data, and you have many options over here, like CIF, PDB, ShellX, Rethan, XYZ, Chem3D, and here is your WASP postcard. Okay, so that's why the Vesta only recognize the postcard files when there is an extension called .wasp in it. If you rename the postcard file to postcard.wasp, it will open the file. Okay, so these are various options that you can explore in the Vesta, and this is how you save files in the Vesta. Okay, and another thing that I want to show you is I have developed a website called Informatics, in which it contains all the information about me. You can visit my website. I will give the link below this tutorial, so you can you can visualize it better in the desktop mode rather than in the mobile phone or cell phone. Okay, So this is my home page. This is my publication page. You can explore all my publications over here, starting from 2014 until 2020. And this is my CV. You can see my infographic CV over here, and this is my YouTube channel as usual. Okay, I have uploaded many videos over here, and these are the news, that some of the physics news or from my university. These are the ongoing projects that I'm working on. These are some of the news you can explore. And this is the gallery, some of my pictorial representation of graphical illustrations of some of my concepts in different publications you can explore here. And these are my guides. He is Professor Rajiv Ahuja, Professor Yogendra Mishra, and I have collaborations with Rodney Ruoff, Professor Ramoti, Jonglin Wong, Ruban Alnis, and these are my researchers, I mean my supporters, who support me in different types of research aspects. Okay, and thank you very much, and wish you a very happy new year. Thanks. Hello people, welcome back to my channel. Today I'm going to talk about the molecular dynamics simulation, how to perform molecular dynamics simulation in Siesta. And also in my all previous videos, as you have seen, that I have mentioned many Siesta algorithms, as well as how to deal with Siesta program that I have mentioned, and also I have done some transport calculations as well. So today my topic would be based upon molecular dynamics simulation, and some of the theoretical concepts that MD simulation performs. So whether you perform the classical dynamics or maybe DFT based dynamics, uh, always it follows one approximation that is called Born-Oppenheimer dynamics, in which you consider nuclei are much slower than the electrons, and we need to extract the information from the potential energy surfaces. We need to find the local versus global minimum. We move over the potential energy surfaces, and good sampling is required for the molecular dynamics simulations. And it also follows the time evolution of a system, solves the Newton's equations of motion, treats in DFT MD, it treats electrons quantum mechanically, and and allows us to study all the dynamic processes, annealing of the complex materials, the influence of temperature, the influence of pressure, and so many parameters influence the molecular dynamics simulations. So there are I'm going to mention you about the how many type of algorithms is in Siesta program. There are, I guess, Verlet algorithm is there, um, which is based upon NVE, microcanonical assembles. Another one is the nose NVT canonical, and NPE, Parinello-Rahman algorithm, and nose Parinello-Rahman algorithm, NPT. So NVE, NVT, NPE, and NPT. Those four types of algorithms are present in, and also annealing options is also there. So in Siesta you have all these algorithms, and I'm going to I mean, if you run with the Verlet, it performs NV ensemble dynamics. If you perform with the nose, it performs NVT dynamics with nose thermostat, I mean temperature based, I guess. And if you perform with Parinello-Rahman, then I guess it pressure PR barostat. It performs the dynamics with the PR barostat. And nose Parinello-Rahman with thermostat and barostat, and anneal with specific pressure as well as that temperature. So these type of algorithms are there, and I'm going to show you how to create the FDF file, input file for the molecular dynamics run. And also I'm going to show some of the outputs that I got from a simple unit cell calculations that I'm going to show. So let's get started, and thanks. And also do subscribe my channel and like my video, share, comment, and also mention that what other videos do you like me to make a tutorial on. Thank you. So let's get started. I recommend everyone to read the Siesta 4.0 or 4.1 manual for the molecular dynamics simulation in Siesta, because all the options have been described well in the Siesta manual. And here are the list of the algorithms that are present in Siesta module. Like if you run for the Verlet, it is a standard Verlet algorithm in molecular dynamics. And another option is the nose MD with temperature controlled by means of a nose thermostat. Perinello-Rehman MD with the pressure controlled by the Perinello-Rehman method. Nose Perinello-Rehman MD is with the temperature which is controlled by the nose thermostat, this algorithm, and the pressure controlled by the Perinello-Rehman method. And anil is another option with the specified desired temperature or the pressure. And these are the 5 algorithms which you can perform the molecular dynamics in Siesta program. And I'm going to show you also what are the options that is available, and I highly recommend everyone to read the Siesta manual before jumping into molecular dynamics simulations. So I'm going to show you some of the options which are used for simulation parameters. Suppose, for example, the tag that you won't need to specify for the molecular dynamics starts with MD and dot and rest of the parameters. So one by one I'm going to show you what are the parameters that you can describe in your input file while calculating Siesta. So number one is the initial time step, which could be the default value is 1. The initial time step would be the first time step would be 1, and the MD dot final time step would be if you need a longer time simulations, then you can mention something around 5,000 or 1,000 or something, whatever. It depends upon the specific requirements. Suppose for 1,000 final step. So another one is MD dot length time step, which is really important because it generates the coordinates or the velocities. It calculates all the MD simulation, the dynamics and the length of the time step of all the MD simulations. So generally people recommend to use, as recommended by Siesta manual, is 1.0 fs. So you can choose whatever you want. It depends upon the desired specific parameters. And another option is the MD initial temperature, and you can specify the room temperatures like 298 Kelvin. And this initial temperature tag can be used with Verlet, nose Perinello-Rehman, nose Perinello-Rehman, and I mean all the options. You can specify the initial temperature, and these 3 options you can specify in all the algorithms as well. And the next option would be MD dot target temperature. that if you need something to be calculated from the room temperature until 600 Kelvin, so you can mention that. And this option can only be used with the nose, parallelogram, nose, parallelogram, and anneal. Only this option can be used only with anneal, nose parallelogram, and nose MD. Not with parallelogram, because it is the pressure controlled by this algorithm. So this target temperature option should be used with anneal, nose parallelogram, and nose MD, not even with Verlet. And another option is called MD tau relax. So this option is only used when you use the anneal MD option, MD type of run, because here you have to specify MD dot type of run. I'll make it type of run, and then you mention all the algorithms. Suppose if you are using Verlet, use Verlet, or if you are using nose, then use nose. If you are using anneal, then use anneal, like that. This is the desired options. Out of all these 5 algorithms, you can specify the MD type of run. And MD tau relax can only be used when using the anneal MD type of run. And okay, and the next would be MD tau relax. The default value is 100 fs, and you can mention whatever the desired parameters that you need to to perform. And this option also performs the target temperature or pressure achieved by the velocity and the unit cell rescaling in a given time determined by this MD tau relax. So, and this option is basically the relaxation time to reach the target temperature and pressure in while using this anneal MD. So this is a relaxation time given to acquire a specific desired temperature or the pressure at a given time. So this option, you need to be careful about this option and use it while using the anneal option over here. Next, if you want to calculate the MD bulk modulus, MD bulk modulus, you have to, again, this option can only be used when you are using the anneal option for the desired temperature and pressure. So while using these 2 tags, you have to mention another tag which is called md.anneal option, and you need to specify pressure and temperature. It should be the other way around, temperature and pressure. This option must be used while using the anneal option. So I'm going to write it again. So MD type of run would be anneal, and you can specify this option. These are the optional options. MD bulk modulus, which is the default value. Default value is I think around 100.0 Rydberg constant BOHR star 3. Yeah, this is the the default options. And yes, MD anneal option can be used for the temperature and pressure for the desired temperature and pressure. You can either choose temperature or pressure, or maybe both, and then you have to mention "and" in between that. Sorry. Temperature and pressure. So these four are the optional parameters for the anneal option. You can use it, according to your choice. And regarding the writing parameters, I can show you some of the FDF files that I have created for different types of run. Suppose for the anneal option, I have created this FDF file, which you have system name, system level, what do you want to label, number of species, number of atoms, chemical species block, lattice constants, lattice vectors, atomic coordinates, Moncost pack, mesh cutoff, basis type, basis size, energy shift, functionals, authors, how many iterations do you require, solution method, and user basis is used when you use the ion files. And these are some of the optional parameters according to your defined choice. The solution method should be diagon. Electronic temperature, you can mention whatever you need. I mean, it depends. And this option is important because it can write the MD history files in the format called MD_char, and you have all your history of coordinates, how it's changing, the coordinates, how it changing. Like suppose you see this is the initial coordinate, and while you go for the second step, it changes the coordinates. So it is required. And also another one, it also produces the MD file, which I'm going to tell you later. So the option would be MD type of run is anneal. Anneal options are temperature and pressure, initial temperature this much, target temperature this much, target pressure also you can mention, length time step, tau relax, and final time step, how many steps do you require. So this option can be used for that I have shown previously. So this is for the anneal option. And now I'm going to show you for the nose thermostat, nose, in which until here everything is same. And here what you define the type of run as nose. Initial temperature is given, target temperature is also given, initial time step, final time steps, and then MD length time step you mentioned for the nose. And for the NPR, nose parallelogram, I think, where is that? Yeah, sorry. FDF file in which you mention the type of run as nose parallelogram, target pressure, and target temperature, because in this algorithm you have the pressure and temperature control, and initial temperature, time step, length time step, and final time step. So this is the nose parallelogram option, and this is the parallelogram option in which you have MD type of run as parallelogram, target pressure, initial time step. You don't have to mention the temperature because it doesn't perform the temperature dependent calculations MD. So only you have to mention the target pressure for the parallelogram. And now for Verlet algorithm, it's really this is the simple algorithm, and you have the options like type of run should be Verlet, initial temperature is 600K, or you mention whatever you initial time step this much, final time spent length time step. So this is the way how you can create the input file for different algorithms. For the 5 algorithms that I have mentioned, Verlet, nose, parallelogram, and anneal options. So And I'm going to show you one output that I got from, I think, Anil options, in which what are the outputs that can be produced in MD. So when you do a calculations, I did a small calculations for the unit cell until 10 time steps. So the most important file that you get over here is ANI file, animation file, the MDE file, the MD car file, and the structure iteration file, eigenvalues file, and XV file where you store all the coordinates. And the most important file is ANI or MD, and then MDE file. So in MDE file, when you open it, so you have, as you have mentioned in the in the input, regarding all the parameters that you need for your calculations. So the first will be the steps mentioned over here. I preferred a small calculations in which I have done only for 10 steps. This is the temperature block, this is the Kohn-Sham energy, this is the total energy, this block, and this is the volume, and this is the pressure. So this is the way how, and also you can use GNU plot to plot each and everything, as x coordinate would be 10 steps, and the temperature, Kohn-Sham energy, E total energy, volume, and pressure would be the y coordinates, as you can mention. So I have prepared out of all the algorithms, when I have done the calculations for the 10 time steps, I get different outputs. And this is for the anneal, this is for the nose thermostat, and this is for the nose parallel step. Okay, and this is for the parallel, in which the temperature doesn't matter but the pressure changes, in which the pressure is mainly controlled here, both temperature and the pressure both controlled. And in the Verlet algorithm, the initial temperature I have mentioned is 600K, and it starts from here, and you can see different all the parameters that you require for your calculations. So one important thing is you have to mention the time step to be longer period, so that you can see some of the outputs. And I'm going to get one output from this calculations by using this algorithm, this utilities from the Siesta, which is called AXSF, which you can visualize how the how the simulation has been performed. And for that, what you need to do is /md to AXSF, just type enter, and you have to specify what is the name system level that you have given. So in my case, I have given anneal, so it has 4 atoms, and suffix of the molecular dynamics file, in which file do you want to visualize the dynamics. So suppose use ANI file, animation file, and you have to specify 3 numbers for the first step, last step, and how many steps interval you need to make your movie. So in my case is 1, 10, and I need it like a 1 time step interval. So do you want to define output box? So I make it no. So you have your file called anil.asxf file. And since I have the Crystal Maker program, which is commercial and can be obtained by spending $80, I guess, and this is really good software. So when you open it, you have your output ASXF file, and also you can open it with xkristen, but xkristen animation is good, but it is not good for the publication quality, I guess. It is only to visualize the output. So this program is really good when you see like this. And when you open the ASXF file in Crystal Maker, just press the button play, and you see how the the dynamics is work on. This is only at a short time interval, only 10 steps. So if you do it for 1,000 or 5,000 or 10,000 steps, you will see the actual animation, how it looks. So this is the way you can predict the output, and you can visualize the output by using whatever the softwares you like, but I like Crystal Maker because it is commercial, and it is well represented and used for publication quality figures. So this is all about the MD simulation. And the most important file, again, I'm going to tell you, is the MDE file, in which you can plot the steps: temperature, Kohn-Sham energy, total energy, volume, and pressure. That's it. And in the next tutorial, this is about the DFT MD simulation. In the next tutorial, I'm going to tell you about the classical MD simulations by using GROMACS. Thanks.
Hello people, welcome to my channel Nerdalytics. A very happy new year to all of you. Let's get straight to the point. Some of my YouTube subscribers, they asked me that they could not find WX Dragon website to be working, and even I found it strange that why uh, WX Dragon site is not working. I mean, uh, this site has not been working since from I think from 1 year. So fortunately, I have downloaded the file WX Dragon, um, executable files previously, like 1 year before, and I kept it in my system for a long time. So when I see that many people have been asking for WX Dragon executable file, then I thought of uploading all of them to my GitHub account, where you can find the repository WX Dragon, and you find all the executable file of WX Dragon. So I'm going to show you how it works. So if you go to WX Dragon, so this is the zip file, or you can say the TBZ extension file, which is this one. And if you click, and it will extract the basic app, which can be used directly on Mac. So if you open it, and you have the window of WX Dragon, and you can directly upload any Postgre file. Suppose say any Postgre, yeah. Open Postgre file, and you can see you can do a multitude of functions with the WX Dragon app by opening Postgre, Contka, Outcar files, etc. And even you can export different modules. For instance, for Siesta, you can get the basic format of the Siesta FTF file, and you can save it to a file. This video, I have uploaded one video regarding WASPKit and WX Dragon previously, so you can have a look into that. Okay, this is for the basic Mac app, but for the Linux, there is an executable file called WX Dragon, which you can see over here. What you have to do is just type chmod plus x WX Dragon in the same folder, and this app is going to and execute by using /WX Dragon, and you can work on it. So yeah, thank you very much. Hello people, welcome to my channel Nerdalytics. I hope you are enjoying a good summer and the sunny weather. So today I'm going to dive you through the analysis, how to do Coupp and COHP analysis using Siesta program, and what are the parameters that you require to analyze Coupp and COHP in Siesta, that I'm going to dive you through. And some of my subscribers, they have asked me to do a tutorial video on this particular analysis. And some of you ask that how you plot Coupp and COHP analysis using WX Dragon, which is not possible in Siesta program, but there are many other programs that can assist you to plot Coupp and COHP by using WX Dragon. So I'm going to dive you through the analysis platform through the Siesta documentation, where how you can perform Coupp and COHP curves for different types of crystal structures that you can go through this website. The link will be given, in the tutorial video. So this is regarding the Siesta documentation. There is another website where the theory behind crystal orbital Hamilton populations and crystal orbital overlap population, which is called Coupp, and COHP is crystal orbital Hamilton populations. You can go through this website where they use a specific program called Lobster, and by analyzing through Lobster, you can plot Coupp and COHP diagrams using WX Dragon, which is possible, but not from the Siesta output. You cannot plot any of the Coupp or COHP diagrams by using WX Dragon if you analyze through Siesta. So I'm going to get you through the parameters that is required. So I have to log into it's all logged in. So the first thing, or the basic thing that you require, is a FDF file where you can define the parameters for any of the crystal structures that you that you want to analyze for Coupp and COHP. So here I'm taking a simple zinc oxide unit cell, and the parameters that is required is, the first and foremost, is system level. So I define it as ZNO, underscore Coupp, and the material, number of species, number of atoms. This is the chemical species level, and these are the lattice vectors, atomic coordinates that you define, your Moncost pack, and these are the default parameters. So I have made many videos how to define the FDF file using Siesta and what are the parameters that you require in order to run a successful Siesta calculations. The first and foremost thing that you require if you want to analyze for the Coupp and COHP analysis is this particular block, which is called Coupp.write. So this can be also visualized by using in the Siesta documentation. Also, if you go here, the most important thing to write in the FDF file is Coupp.write, that you have to set true in this case. So if you go, yes, this one. So just you have to define this, and the rest of the parameters that is required you have to input by using FDF file. So I'll give this FDF file on my on my GitHub channel, where you can find all the different parameters. So yeah, the basic thing that you require is Coupp.write true, and you have to run the calculations. I think I have ran already the calculations. So the two most important file which is required to perform the Coupp and COHP analysis is this one, WFSX, and another one is HSX. Okay, this contains all the wave function files, and this contains the the overlap population files. So these two files you have to copy to a directory called Coupp, and you have to rename this particular file, WFSX file, to ZNO underscore Coupp.wfsx, not the full one. This full brilliant zone which is given here, you have to delete that. You have to rename it just to WFSX, and HSX file will remain the same. And another important thing that you require for the Coupp and COHP analysis is Zeno MPR file, in which you have to define the system level, which you have input here in this particular, what is that? Yeah, in the FDF file where you put the system level as Zeno Coupp. So the same thing you have to define over here. And if you you are going to analyze the Coupp and COHP analysis, so you have to input COOP over here. And the next thing, which is the most important thing, you need to analyze between there are two atoms in this particular unit cell, which is number one is zinc and another one is oxygen. So you want to analyze the bonding and anti-bonding characteristic between zinc and oxygen. And similarly, you can input that Zn-O, and you have to input zinc, and between the oxygen, this is the bond length. So this bond length you can get it from bonds file, which is over here, the final bonds. If you go here, so it defines the range of the bonding characteristics between these two. So generally, you don't have to define particularly these values which is shown over here, but you can define a range. So in this case, I have defined a range 0.25 to 3.05. And similarly, not only the atoms but also the orbitals you can define, like 3D orbitals of zinc and 2p orbitals of oxygen. And in between these two, you have to analyze the bonding and antibonding characteristics. So similarly, with all the orbitals, you can define the parameters. So if it's done, then we go to the Coupp, and there is a particular tool in Siesta Utilities. So if you go over here and if you go to the GitLab directory of Siesta, you will find this particular utility called mprop. I think in the utils directory, if you go for the Coupp, yeah, here you can find this mprop.f90. You have to, install this, or if you have installed the Siesta program, this will be automatically installed, so you don't have to do anything. And I would recommend you all to use 4.1.5 version of Siesta, which has much better features, and they have a lot of updated parameters, I would say, and you can get everything over here. I have shown many videos on transport calculations as well, so I would recommend everyone to use 4.1.5 version rather than the previous versions, because it has much improved algorithms and much defined, I would say the well-defined parameters, and the documentation is really good. So you can go here, this mprop tutorial. If you type mprop -h, you will get the documentation of mprop, basically. So the first and foremost thing that you want to do for the mprop analysis is, so this is the smearing parameters. So you can define 0.2 to 0.5, and m is the, so if you go through the documentation, I would say, so yeah, this is the lower bound of the eigenvalue range, and this is the upper bound of the eigenvalue range, minus m and minus capital M. And this is the n number of points that you require to plot the values, and that's it. And you define the this zno.npr file. So I'm going to show you how to do that. So yeah, basically this is the smearing parameter, and you can define here the number of points as well. So in this case, I put 2000. The default is 200 in this case. And this is defined -20 to +20 range. And you don't have to define the .mpr over here. You just have to define the name, which is zinc oxide in this case. So if you run this, yeah. So this is how you do the COP and COHP analysis. And one of the, if you want to plot the Coupp and COHP, so I think XM Grace is one of the best tool to plot uh, the Coupp and COHP. So if you drag this, so if you see over here, yeah, you get the nice plot of this is between 3D orbitals and the 2p orbitals of the Coupp, and you can put as many as number of you know the parameters that you have defined over here. Suppose zinc and oxygen, 3d and 2p orbitals, 4s and 2s orbitals, etc. So what you have to do, you just have to drag and drop. So you take the Coupp of over here, yeah, that's it, and you plot it. Yeah, this is you get. So basically, how you analyze the Coupp and COHP and how to understand this is generally it is recommended that if the values are positive, that means they are having bonding characteristics. If they are having negative values, that means those are anti-bonding analysis. So you can read the documentation over here in this particular example. They have defined a well-defined characters, well-defined features, and how to use it, and how you can download the program. And one or more important things is WX Dragon is available over here for Windows and Linux users. You can run the analysis using Lobster and then plot the results using WX Dragon. And if you want to read the theory, they have given a very nice explanation how to analyze Coupp and COHP, and also simultaneously the DOS, how you can compare the DOS with the COHP analysis. Right, so that's it for the video. I think it should not have been a problem because this is really straightforward and very easy to use, and Siesta has improved a lot. I would recommend you all to go through the Siesta documentation and do a dive in to the utils directory. Sorry, the utils directory where you find many different utilities that is implemented in Siesta 1.5, 4.1.5, and I hope you like my video, and please subscribe to my channel. Oh yes, and one more important thing is if you want to see where the WX Dragon has been improved and how it can be utilized to plot the COP and COHP analysis, is that so if you go over here, anything, so let me see. So you have to open any crystal structure over here, per se any XYZ file. Then I think here you can see that there are many other options for Lobster, WASP, Gulp, LMTO. So this is the Lobster that I have been talking about, where you can uh, calculate by using Lobster, and then you can plot by using WX Dragon. So this is how you plot. You cannot use WX Dragon for the Siesta output files, which is very difficult over here. But I would recommend go for WASP or go for Lobster, and you can plot the similar diagram related to this one particularly. Something like, I think theory has been given over here. Oh, sorry, this one. Yeah, you can plot like this, I guess. I guess by using double X dragon, you can plot this kind of diagrams. So I'm not sure. I haven't used Lobster, but you can use double X dragon for this particular analysis, and that's it. Thank you very much.